Oh, is the camera on? Hi friends, I'm sure all of you have used a mirror. We use a mirror since it's a reflector of light. But do the other objects also reflect light? Do you know what are the laws of reflection? What is a regular and scattered reflection? All this is coming up in this video. And then we'll finish off with our top 3 questions on this topic. You must be familiar with what is reflection of light. Reflection of light is the bouncing back of light after hitting a surface. Let's visualize it using this ball here. So if you imagine light to be this ball, can you see that it's bouncing back from the mirror or it's getting reflected by the mirror? The mirror that we are discussing in this video is a plane mirror. It has a flat surface. The mirror is shiny and opaque. Do you know how a mirror is made? You need to take a thin layer of glass and put a layer of silver on one side. The silver side reflects the light but does not let it pass through. An ideal mirror would reflect back all the light. But a real mirror absorbs some of the light energy and the remaining gets reflected back. Light follows certain laws of reflection. But before we discuss the laws of reflection, let's do a quick recap on the basic terms first. Let's say there's a mirror here and I shine this torch towards the mirror. The torch gives out a beam of light. A beam is a collection of light rays. Let's consider a single ray of light for simplicity. The ray of light that's falling on the mirror is called incident ray. The point where the incident ray hits the mirror is called the point of incidence. And the ray that comes back is called the reflected ray. Now we can draw an imaginary line at the point of incidence that is perpendicular to the mirror. And this line is called the normal. The normal is used to measure the angles here. So the angle the incident ray makes with the normal is called the angle of incidence. And similarly, the angle the reflected ray makes with the normal is called the angle of reflection. There are 2 laws of reflection. The first law states that the incident ray, the reflected ray, and the normal at the point of incidence all lie on the same plane. Now, what does this long sentence mean? Let's take a closer look. The first law talks about the incident ray, the reflected ray, and the normal. All these 3 things lie on the same plane. Now, what does plane mean? Plane is a flat surface, just like a sheet of paper or a table surface. So, which plane are they talking about here? This is a common confusion. Is it the mirror? That's right, it's not the mirror. In fact, the first law doesn't even talk about the mirror. It's this flat surface that is perpendicular to the mirror. And as you can see, the incident ray, the reflected ray, and the normal are all lying on this flat surface, which is our plane here. The second law of reflection, thankfully, is much easier. It states that the angle of incidence is equal to the angle of reflection. As you can see in the picture here, the angle of incidence is 40 degrees, and so is the angle of reflection. Now, if I change the angle of incidence by moving this torch, as you can see, the angle of reflection also changes, so that the angle of incidence is always equal to the angle of reflection. Let's place the 2 laws of reflection of light on our concept board. When we talk about reflection of light, what's the first thing that comes to your mind? You must be thinking about a mirror, right? But do the other objects also reflect light? For example, if you look around in the room, do the table, chairs, walls, even you and me, are we reflectors of light? The answer is yes. because that's how we see the world around us. These objects do not have light of their own. They are reflecting the light coming from some luminous source, like the sun or a light bulb. As we discussed, all objects reflect light. Now an interesting question is, do all the objects reflect the light in the same way? What do you think? So if you compare a mirror and a sheet of paper, do they reflect the light in the same manner? If that's true, then I don't need to buy a mirror, right? I can just comb my hair using a sheet of paper. But we know that's not the case. So let's go ahead and talk about the types of reflection. There are two types of reflection. One is regular reflection and second is irregular or scattered or diffused reflection. A mirror or a highly polished surface is an example of regular reflection. But most of the objects around us, like paper, walls, curtains, are all examples of irregular reflectors of light because they scatter the light. It's easy to understand the difference between regular and irregular reflection if we consider a parallel beam of light falling on a mirror and a surface like a paper. So let's look at the mirror case first. So as you can see in the plane mirror, the parallel beam remains parallel even after reflection. So if you look closely, you can see that all the rays in the beam have the same angle of incidence. And following the laws of reflection, all the rays will have the same angle of reflection. So the incident beam remains parallel even after reflection. Now let's look at the case of irregular reflection. When a parallel beam of light falls on a surface like a paper, as you can see, it gets scattered in different directions. Is this because the laws of reflection don't hold here? No, the laws of reflection always hold. The paper seems smooth, but if we look closely at a microscopic level, the paper is rough. So as you can see here, the angle of incidence for the different rays in the beam are different. And so the angles of reflection will also be different. And this is how the light gets scattered in different directions. So it's called scattered reflection. Know that mirrors are of different types: plane mirror and curved or spherical mirrors. Spherical mirrors can be further divided into concave mirror and convex mirror. So there are three types of mirrors: plane, concave and convex. In fact, I have all these three mirrors on this wall here for you. I'm going to go and stand in front of each of these mirrors and let's see what do we observe. If I stand in front of the first mirror, I appear to be the same height. If I stand in front of the second mirror, oops, I appear to be inverted. Now if I move close to the mirror, I appear to be magnified. Now if I stand in front of the third mirror, I appear to be shorter. Can you guess the type of mirror for each of these? That's right. The first mirror is a plane mirror. The second mirror is a concave mirror. And the third mirror is a convex mirror. Let's talk about the three mirrors. A plane mirror has a plane or flat surface. And I'm sure you must have noticed that when you stand in front of a plane mirror, you appear to be the same height. Now let's look at concave and convex mirrors. These mirrors are curved mirrors. And a very simple way to understand them is using a spoon. So I'd like you to pause the video right here and go and get a spoon. And it'll be great if you can get a large and shiny spoon. So are you ready with your spoon? A concave mirror is curved inwards. So if you look at this side of the spoon, can you see it is curved inwards just like a concave mirror. Now hold the spoon like this and look at yourself in the spoon. What do you observe? You appear to be inverted and smaller in size or diminished. Now if you bring the spoon really close to yourself, you can see that you are looking magnified. But an easier way to do this is to hold an object like a pencil and get it really close to the mirror. Now you can clearly see the magnification. So a concave mirror is the only mirror that can produce an inverted image in this position or a magnified image. A convex mirror is the opposite of a concave mirror. So if we flip the spoon, here we have a convex mirror. Now if you look at yourself on the convex side of the spoon, what do you notice? You appear to be smaller, but your image is now straight or upright. And no matter where you move the spoon, the image in a convex mirror is always diminished and upright. So this was our quick recap on the three mirrors. More details on spherical mirrors coming up later in the video. But first let me ask you, which types of mirrors are you using in your daily lives? I'm using all three types of mirrors every day. If you don't believe me, I'll be showing you some clippings from my daily life. And you need to be a detective and identify the type of mirror. Is it a plane mirror, concave mirror, or a convex mirror? Are you ready? Let's start. In the morning, when I shave, which type of mirror am I using? The shaving mirror is a concave mirror. The face in the mirror is magnified. If I flip this mirror, there's a plane mirror behind this. Can you see the difference in magnification between the plane mirror and the concave mirror? When I comb my hair, which type of mirror am I using? This mirror has a flat surface. It's a plane mirror. When I leave the house and go down in the elevator, which mirror does the elevator have? It's a plane mirror. To save time, I can actually comb my hair on the way down. While driving the car, I use the two mirrors, the rear view mirror and the side mirror. Which types of mirrors are these two mirrors? That's right. The rear view mirror and the side mirror are examples of convex mirrors because they give a greater field of view. There are mirrors kept at road intersections so that you can see the vehicles coming from the other side. Which type of mirror are these? That's right, convex mirrors. So as you can see, I'm using all three types of mirrors every day: plane, concave and convex mirrors. Concave and convex mirrors are together called spherical mirrors. Now do you know why they are called spherical mirrors? If I take this ball, it has the shape of a sphere. Now let's imagine the surface of this ball to be shiny like a mirror. I wish I had a silver colored ball, then it would actually look like a mirror. Now if I take this knife and I cut the ball here, this slice is a curved mirror. It's called a spherical mirror since it's come from a sphere. If the inside portion is polished, it's called a concave mirror. If you polish the outside portion, it's called a convex mirror. An easy way to remember the concave mirror is, it's as if you're entering a cave. It's a hollow portion. So this side is a concave mirror and the opposite side, which is bulging, is a convex mirror. The concave mirror can be represented by this simple diagram where the smooth side is the shiny reflecting surface. The side with these small dashed lines is the back of the mirror. Similarly, for the convex mirror, the smooth side is the shiny reflecting surface and this side is the back of the mirror. Now an interesting question is why these mirrors behave differently. To understand, let's imagine we are throwing a parallel beam of light on all the three mirrors. Let's start with the plane mirror. So if you throw the parallel beam of light, can you see that the light rays remain parallel even after reflection? Next, let's try the concave mirror. Now if you throw the parallel beam of light, can you see that the concave mirror converges the light rays to a point? The concave mirror is a converging mirror. And now let's look at the convex mirror. So if you throw the parallel beam again, can you see that the convex mirror is diverging the light rays? So the convex mirror has a diverging action. It's a diverging mirror. Here's a comparison table of a plane, concave and convex mirror. Now you must be thinking, why curved mirrors converge and diverge light rays but a plane mirror does not? Is it because these laws of reflection hold only for a plane mirror and not for curved or spherical mirrors? What do you think? The answer is the laws of reflection always hold for both plane and curved mirrors. Let's take a closer look. So if you draw the normals at each of the points of incidence for the light rays, the angle of incidence is always equal to the angle of reflection. But the concave and convex mirror have a converging and diverging action because of their curved shape. It's due to their curvature that the light rays reflect in this manner. There are some important terms for spherical mirrors. For example, pole, focus, center of curvature, principal axis, and so on. Let's understand these terms with the help of a simple diagram. Let's start with the concave mirror. The center of curvature is the center of the hollow sphere of which the mirror is a part. The center of curvature is represented by C. The center of the surface of the concave mirror is called the pole, represented by P here. Radius of curvature R is the radius of this sphere. The straight line passing through the center of curvature and the pole is called the principal axis. The portion of the mirror where the reflection of light takes place is called the aperture of the mirror, represented by mm dash here. Remember, the concave mirror is a converging mirror. If a beam of light that is parallel to the principal axis is incident on the concave mirror, after reflection, the rays meet at a point on the principal axis. This point is called the focus, represented by F. The focus is exactly in the center of P and C. The focal length F is the distance between the pole and the focus. So focal length equals radius of curvature by 2. Now let's take a look at the convex mirror. Center of curvature is the center of the hollow sphere of which the mirror is a part, represented by C here. Note that the center of curvature of a convex mirror lies behind the mirror. The center of the surface of a convex mirror is called the pole, represented by P here. Radius of curvature R is the radius of this sphere. The straight line passing through the center of curvature and pole is called the principal axis. The portion of the mirror where the reflection of light takes place is called the aperture, represented by mm dash here. Remember, the convex mirror is a diverging mirror. If a beam of light that is parallel to the principal axis is incident on the convex mirror, after reflection, the rays appear to diverge from a point on the principal axis. This point is called the focus, represented by F. The convex mirror has a virtual focus since the focus lies behind the mirror. The focus is exactly in the center of P and C. The focal length F is the distance between the pole and the focus. So focal length equals radius of curvature by 2. Let's place the label diagram of a concave and convex mirror on our concept board. Now that we are done with the concepts, are you ready for the top 3 questions on this topic coming up for you right now? Friends, try solving these questions and let me know your answers and doubts by putting it in the comments below. I make a commitment to reply to all your comments as soon as possible. So I'm going to disappear and you pause the video here and give these questions a shot. I hope the concept of spherical mirrors is super clear to you now. Remember, our spoon is both a concave and a convex mirror. I would also encourage you to look for the different types of mirrors in your daily lives. For example, do you know the torch has a mirror inside it? Which type of mirror is that? And what about the mirror in your dentist's office? Or the mirror on the streets and in the street lights? Do let me know what you find by putting it in the comments below. If you stand in front of a plain mirror, do you know exactly where your image will be formed? That's right, it's going to be behind the mirror. The distance between the image and the mirror will be exactly same as the distance between you and the mirror. We also know the properties of the image. It's going to be virtual and upright, and the image will be the same height as you. But now if I replace the plane mirror with a concave mirror, can we predict where the image will be formed? It's not so easy now. Or if I replace it with a convex mirror, where will the image be formed? What will its properties be? In this video, I'm going to make the topic of image formation for spherical mirrors, that is the concave and convex mirrors, really easy for you. And as usual, we'll finish off with our top 3 questions on this topic. Before we look at spherical mirrors, let's do a quick recap on how to draw the ray diagram for a plane mirror. As we discussed, we know all the properties of the image formed by a plane mirror. Image height equals object height and image distance equals the object distance. So we can cheat here. We first draw the image and then we draw the light rays and produce them backwards to match the image. We take 2 rays from each point on the object because you need a minimum of 2 rays to obtain a point on the image. So for a plane mirror, the image is drawn first and then the light rays. But we can't do this for a concave or a convex mirror because we are not sure of the properties of the image. We must use the light rays and the light ray rules for obtaining an image for spherical mirrors. Let's start with the concave mirror. The concave mirror is a converging mirror. For image formation, we need to draw the concave mirror accurately. Let me show you a simple trick for that. Draw a line representing the principal axis. Using a ruler, mark 3 points where C is at 0 cm, F is at 3 cm and P is at 6 cm. You can take any convenient distance. F should be exactly in the middle such that CF equal to FP. C is the center of curvature, F is the focus and P is the pole of the mirror. Now use your compass to draw an arc for the concave mirror. The compass point should be placed at C, the center of curvature, and the radius of the arc will be CP, which is equal to 6 centimeters in this case. Mark the back side of the mirror with these dashes. Now let's talk about the rules for image formation of a concave mirror. Light is a very visual topic, so I suggest you to keep pausing the video and drawing the ray diagrams for these rules in your notebook. Then you'll get a better feel of what is going on. There are 4 rules for a concave mirror, so let's take a look at them. Rule 1. a ray of light which is parallel to the principal axis after reflection passes through the focus. Rule 2. A ray of light passing through the center of curvature is reflected back along the same path. Do you know why? That's right. The ray of light falls normally, perpendicular to the mirror. That's why it's reflected back along the same path. Rule 3. A ray of light passing through the focus after reflection becomes parallel to the principal axis. Can you see that rule 3 is exactly opposite of rule 1? It's due to reversibility of light. Rule 4. A ray of light which is incident at the pole of a concave mirror is reflected back, making the same angle with the principal axis. It looks like a plane mirror type of diagram since the principal axis is like the normal here and the angle of incidence is equal to the angle of reflection. Let's place the 4 rules that we have learned for concave mirrors on our concept board. Remember, when drawing an image, you need 2 rays from a point on the object. So for concave mirrors, you need to select 2 rules that are convenient for the diagram. Now an important note here is, avoid using the 4th rule unless really necessary, because it's hard to measure angles accurately with your protractor. So it can lead to inaccuracies in the diagram. So basically you need to use 2 out of the first 3 rules for concave mirrors. Now I'm going to be the object and I'll go and stand in front of the concave mirror and you need to find my image. So are you ready? Let's try it out. Here I am on the principal axis. I'm far away from the concave mirror. I'm going to walk towards the mirror and stand on different places on the principal axis. And you'll see that the image will change based on my location. So let's start with case 1. I'm beyond C, the center of curvature. You need to consider the rays from the top of the object. So from my head. And remember, we need to take 2 out of the first 3 rules. So let's use rule 1. For the ray that is parallel to the principal axis, after reflection, it passes through the focus. And for the second ray, we can use rule 2. So the ray passing through the center of curvature gets reflected back along the same path. Now what does the intersection of these 2 reflected rays represent? That's right, it's the image, and it's the image of my head, because we started with the rays from the top of the object. Now where is the feet in my image? You don't need to draw the rays for that. The feet lie on the principal axis. So we can simply extend the image to the principal axis and find the bottom of the image. So as you can see here, using the ray diagram, we have found the position of my image. What are the properties of the image? There are 3 points here. Is the image real and inverted, or is it virtual and upright? Is the image magnified, diminished, or is it the same size as the object? And what is the position of the image? So let's see what are the properties of the image for case 1. As you can see here, the image is real and inverted. It's real because it's formed by the real intersection of light rays. And it's upside down. So it's an inverted image. As you can see, the image is diminished because it's smaller than the size of the object. And the position of the image is, it's located between the center of curvature and the focus. You'll find similar diagrams in your textbook. Of course, I won't be the object there. Usually we use an up arrow to represent the object, and it's marked as AB. And the image is also going to be an arrow and marked as A', B'. Here the arrow of the image is inverted since it's an inverted image. Now let me walk closer to the mirror. I am going to stand at C, the center of curvature for our case 2. Once again, let's draw the rays from the top of the object. We need to use 2 rules from the first 3 rules. So for our first ray, let's use rule 1. The ray that is parallel to the principal axis after reflection passes through the focus. Now I can't use rule 2 since I am standing on the center of curvature. So let's go ahead and use rule 3. The ray that is passing through the focus after reflection is parallel to the principal axis. So this is our second ray here. Where is my image? As you can see here, it's exactly below me. What is the nature or properties of the image? It's real and it's inverted. It's the same size as the object, so the same height as me, and its position is at the center of curvature. If you try drawing the ray diagram for this case 2, where the object is at the center of curvature, you might find that you're not getting the image exactly at the center of curvature. Now this can happen if the focus F is not exactly between P and C, or if the rays are not drawn very accurately. So to avoid such errors, an important exam tip is to use the cheating trick, just like we did in plane mirrors. So you first draw the inverted image at the center of curvature, and the image height is equal to the object height, and then you draw the rays. So then you'll get the image accurately. Now I'm going to move closer to the mirror. So this is our case 3, where the object is between the center of curvature and the focus. I would like you to pause the video here and find the image yourself using a ray diagram. Also write down the properties of the image formed. So what is the nature of the image you got? That's right. The correct answer is it's a real and inverted image that's magnified. So this is the ray diagram, and as you can see, the position of the image is beyond the center of curvature. Now I'll move ahead and I'm going to stand at the focus of the concave mirror. Again, let's use 2 rules out of 3. As you can see, this is an interesting case because the reflected rays are parallel. The reflected rays never meet. So our image is formed really far away at infinity. The image is real and inverted, and it's highly magnified. Now let's look at the last case where I move really close to the mirror. The object, that is me, is between the pole and the focus here. Now let's use rule 1 and rule 2 to draw the light rays from the top of the object. And as you can see here, the reflected rays are divergent. So let's produce them backwards to obtain our image. Wow! Can you see? I'm magnified here. So what are the properties of the image? The image is virtual and erect. It's magnified, and as you can see, it's formed behind the mirror. Do you know how the concave mirror is used in this case? That's right, it's used as a shaving mirror. Since you appear magnified, it's much easier to shave. Now that we are done with the topic of concave mirrors, let's take a look at the other type of spherical mirrors, the convex mirrors. The convex mirror is a diverging mirror. For image formation, we need to draw the convex mirror accurately. Similar to the concave mirror, draw a line representing the principal axis. Using a ruler, mark 3 points where P is at 0 cm, F is at 3 cm and C is at 6 cm. You can take any convenient distance as long as F is exactly in the middle between P and C. So the distance CF is equal to FP. P is the pole of the mirror, F is the focus, and C is the center of curvature of the mirror here. Note that in a convex mirror, the F and C are on the opposite side compared to a concave mirror. Now use your compass to draw an arc for the convex mirror. The compass point should be placed at C, the center of curvature. The radius of the arc will be Cp equal to 6 centimeters in this case. Mark the back side of the mirror with these dashed lines. Now let's talk about the rules for image formation of a convex mirror. Just like concave mirrors, there are 4 rules for a convex mirror. Rule 1. A ray of light which is parallel to the principal axis, after reflection, it appears to be coming from the focus. Can you see that the real rays are shown in solid lines and those behind the mirror are shown with a dashed line? Rule 2. A ray of light going towards the center of curvature of a convex mirror is reflected back along the same path. Rule 3. A ray of light going towards the focus after reflection becomes parallel to the principal axis. Can you see that Rule 3 is exactly opposite of Rule 1? It's due to reversibility of light. Rule 4. A ray of light which is incident at the pole of a convex mirror is reflected back, making the same angle with the principal axis. Here the angle of incidence is equal to the angle of reflection. Let's place the 4 rules that we have learned for convex mirrors on our concept board. Similar to concave mirrors, avoid using the 4th rule unless really necessary, because measuring angles accurately with your protractor is hard and it can lead to inaccuracies in your diagram. So basically you need to select 2 out of the first 3 rules for convex mirrors. Once again, I'm going to be the object and I'll go and stand in front of the convex mirror and you need to find my image. So are you ready? Let's go ahead and try it out. Here I am on the principal axis at a certain distance from the convex mirror. Again, we need to take the light rays from the top of the object. So my head. Remember, we need to use 2 rules from the first 3 rules. So for the first ray, let's use Rule 1. The light ray that is parallel to the principal axis after reflection appears to be coming from the focus. And for the second ray, let's use Rule 2. The light ray which is going towards the center of curvature gets reflected back along the same path. Now where do these 2 reflected rays meet? The reflected rays are divergent here, so we need to produce them backwards. And the point where they meet is the position of the image of my head, since we considered the rays from the top of the object. Now where are the feet in my image? That's right, on the principal axis. So we simply need to extend the image down to the principal axis and we get the bottom of the image. So you don't need to draw rays for that. And as you can see from this ray diagram, we have found the position of my image. What are the properties of the image formed here? The image is virtual and upright. It's virtual because it's formed by the reflected rays extended backwards. The image is diminished and as you can see, it's formed behind the mirror. Now let me walk closer to the convex mirror. Again, we are going to use 2 out of the 3 rules to obtain our image. And as you can see, the image formed has similar properties. It's virtual and erect, it's diminished, and it's formed behind the mirror. Remember, the concave mirror had so many different cases, but the convex mirror is the easy one in the syllabus because it doesn't matter where you stand in front of the mirror, the image properties are always going to be the same. It's going to be virtual and erect, diminished, and the image will be formed behind the mirror. Have you noticed the convex mirrors used at the intersection of roads? What is the nature of the image produced in the convex mirror? That's right, it's always virtual, upright, and diminished. Imagine if that convex mirror gave an inverted image, then the driver would get all confused and an accident may happen. So the convex mirror always produces a virtual, upright, and diminished image. I hope the image formation for concave and convex mirrors is super clear to you now. So let's start off with a very simple puzzle. What goes through water without getting wet? So what is your answer going to be here? What do you guys think? What goes through water without getting wet? So we can see the correct answer here is going to be light, even sound. Absolutely right. What can go through water? Light, sound, without getting wet. Why? Because these are not matter, these are forms of energy. So they can pass through water but they don't get wet. And of course we are going to be dealing with a lot of light today with reflection of light topic. Very good. Inyan Ramraj is also saying radiation. Excellent. Yes, because light is an electromagnetic wave. It's like a form of radiation. So when we talk about light, let's understand this concept of ray and beam of light very clearly. Okay, like you can see the light is switched on in your room or if you take a lamp or a torch. So a simple example is if you take a torch like this, have you guys seen this? You can see this kind of beam, what we call, like this kind of layer of light. Okay, so that is called a beam of light. Or when you see the vehicles, the bikes and the cars, you can see their beams, especially against in the pollution or the dust, the beam is more clearly visible. So this is what we call as that spread of light, right? This column of light that comes through is called the beam of light. Now when we talk about the beam, we can imagine that the beam is made up of many thin lines of light, or what we call as a ray of light. Now how do you understand a ray? If you imagine you take this torch and you cover it with a black paper. So you cover the torch with a black paper and there is a tiny hole over here. There's a small tiny hole here. So then you can imagine this kind of line of light is coming out through this tiny hole. Okay, and this is what we call as the ray of light. What is the thickness of this ray? Or if I ask you in mathematics, what is the thickness of a line? Does a line have a thickness? No, it's absolutely right. It has a length but no thickness. Same way, ray has no thickness. So it is sort of an imaginary concept, right? You can't really see one single ray. So even if some of you might be thinking, okay, what if I talk about a laser pointer? Does a laser pointer throw a ray of light or a beam of light? If you take a laser pointer, will it throw a ray of light or beam of light? Again, it is very thin, but even that thin thing is a beam of light. Very good, it's a beam of light, absolutely right, made of many thin rays. Okay, so it is almost technically impossible to get a single ray, but by drawing this line, it makes the concept easy, considering light as a ray. And we know light travels in a straight line when it's going in one medium. So rectilinear propagation of light means we are talking about a straight ray, thin line of light. And beam is a collection of many rays. So you can see that beam is made up of many rays. It's a collection of all these rays. So please keep this important concept in mind. Rays like this line of light, and we always make it travel in a straight line, and this is a collection. Beam is a collection of the rays. How do we know we are dealing with a ray or a beam? Normally when you have a light source, you will automatically have a beam, but we consider some parts of it, or we consider a line of it, so a ray. So as we'll see in the ray diagrams, we consider the the extreme ends. So if you talk about this beam, if I consider this top ray and the bottom ray, right? So I can understand there's light in the middle. So there, to make it easy, we have considered only 2 rays. You can consider 3, 4 rays. Actually, a beam has how many rays? Can you guys tell me? A beam is made up of how many rays? 1, 2, 3, 4, how many? What do you guys think? Basushri has the correct answer. Ishan has the right answer. Rohit, Aditi Shukla, Ghost Rider, please change your name to your real name. Shaurya Gupta, Vijay Lakshmi, yes, uncountable. Absolutely right. The correct answer is infinite or uncountable. A beam is made up of many lines or rays of light. Okay, so beam is infinite or infinite rays. Beam can be divided into 3 types of beams. You could have rays like this, where what do you see over here? Here you can see that all these rays are parallel to each other. So this is what is known as a parallel beam, where the rays of light are parallel to each other. Now you could have that maybe the rays of light are coming out of this point. They are emerging from this point and spreading away. So what do you call this type of beam? Where the rays of light are spreading away. So when we say spread, we use the word diverges. Okay, very good. So this is known as a divergent beam. And when the rays are meeting at a point, so if you have rays of light going and meeting at a point here, then what do you call this kind of beam? So again, it's a beam because a beam is a collection of one or more than one rays, right? Actually infinite rays, but we consider, for simplicity, we consider a few. So if we consider, again, beam is a collection of rays. So here what we can see, that they are meeting at one point. So this is called a convergent beam, because we can say, or converging beam, right? We can say it converges to a point. So diverging means spreading away, converging is the opposite, rays of light meeting at a single point. So now let's talk about reflection of light, because we're going to look at reflection topic. What is the meaning of reflection of light? So all of you know a mirror, and what is the definition? Reflection is the bouncing back of light rays after hitting a surface. Just like if you take a ball and you hit it on the wall, it bounces back. Same thing is happening here when light rays are hitting a mirror surface. So when light rays are coming like this, they're hitting a mirror surface, they're bouncing back from it, right? So they're hitting and bouncing off it. So if you draw it over here, when light rays hit a mirror surface, so what will happen? These light rays will bounce off, right? So they'll bounce back. So they'll not go through, because a mirror is opaque, it is not transparent. So light is not going to simply go through the mirror, it is going to bounce back from the mirror. So it's going to go like this. So this is the meaning of reflection of light. And mirror, we always draw it like this. We draw a straight line, and these dashed lines means this is the back of the mirror. This flat plain side is the reflecting surface of the mirror. So remember the laws of reflection. You have studied this in the lower classes as well. That what are the laws of reflection? The incident ray, there are 2 laws, right? First law and second law. The first law says the incident ray, the reflected ray, and the normal at the point of incidence all lie on the same plane. First law is the little difficult one. Let's understand it. Okay. So what is happening here? The ray that is falling on the mirror. So here I've taken a simple single ray, right? Not a beam. I've just taken one ray here. When it is falling on the mirror, this is called the incident ray, because it is one which is incident on the mirror. So this is my incident ray. And you know what happens? When it hits the mirror, it's going to bounce off it, right? So this will happen something like this here. And we always draw these arrows. Please remember, drawing the arrow is very important. In fact, my physics teacher used to give us 0 if we had a ray diagram without arrows, because like you know in mathematics, ray has a direction. So here we are showing the direction of the light. Here you can see the light is going downwards. After reflection, it bounces off. So make sure you guys draw those arrows, not just simple lines, right? Ray, we draw it always with the arrow. So this is the incident ray. After reflection, what is this ray called? obviously this will be called the reflected ray. And the normal, what is the normal here? Normal means it's not a ray, but it's an imaginary line that is drawn perpendicular to the mirror. Normal is an imaginary line drawn perpendicular to the mirror. So let's draw it. So normal will look something like this. An imaginary line drawn at the point of incidence and perpendicular to the mirror. So something like this. This is our point of incidence where the incident ray hits. So all of you can see, and we can label this normal as n dash, and let's call this the normal. I have shown it with the dotted line because it is an imaginary line. Now what is our first law saying? The incident ray, the reflected ray and the normal all lie on the same plane. This is the thing that confuses most students. Where is this same plane here? First of all, what does a plane mean? Here we are not talking about the aeroplane, right? What is a plane? Plane in mathematics or physics means a flat surface, right? So just like if you see your table surface or your laptop or tablet, that plane is the flat surface or the floor here, right? Plane. So can you guys tell me where is this flat surface that the first law is talking about? The incident ray, the reflected ray and the normal at the point of incidence. So point of incidence is this O here. So point of incidence O, okay. So where do they lie on the same plane? Is the same plane the mirror? Do you guys think the plane is the mirror here? Yes or no? What do you guys think? If I label the mirror as mm dash, is that my plane? See, the first law doesn't even talk about the mirror. Otherwise they would have said mirror, right? So look at the law. It says the incident ray, the reflected ray and the normal at the point of incidence all lie on the same mirror. They would have written. No, they said same plane. So plane is not the mirror here. Then where is the plane? So the question is, where are they lying on? So just like when you are sleeping, you lie on a bed, right? So bed is your plane, it's your flat surface, you lie on the bed and sleep. Here, where is the incident ray, the normal ray and the reflected ray lying? Where are they lying? Where is their bed? You can see this flat surface. Very good. Basically the digital board here, right? Or if you draw this diagram on your paper, it is your paper, your copy, right? That paper, that is the flat surface. So basically when we are talking about the plane, it is this whole area. This is our plane. This thing, right? Because can you see the incident ray, the normal and reflected ray are all lying on this flat digital board. What does it mean that they are not, they are in the same plane? Is it that incident ray is like this and reflected ray is coming out in 3D, coming out of the digital board? No, it is lying on the same flat surface. Normal also is drawn on the same flat surface. It is not outside, correct? So this is very important concept, that this is the plane here. Okay, so first law is done. Let's look at the second law, which is thankfully much simpler than the first law. I could never remember that whole sentence, incident ray, reflected ray and the normal at the point of incidence all lie on the same plane. Too many words there. But now I hope you have understood it. Now let's look at the second one. Angle of incidence equal to angle of reflection. Okay. One very important thing is, normally when we measure angles in geometry, we measure like this, right? But not in physics. Angles are measured with the normal. Okay. So when we are talking about the angle of incidence here, the angle of incidence is going to be this angle. The angle between the incident ray and the normal. And I'm going to mark it as I. So this is my angle of incidence I. And then the reflected ray and the normal. So this is going to be my angle of reflection R. So the second law is basically telling us angle I is always going to be equal to angle R. Never slightly less or more, always equal. Which means if you measure this with the protractor. So let's say you take a protractor here. Do we have a protractor here? There you go. So if you take a protractor and you measure this angle, so how will you have to measure it? You will have to place it against with the normal. Then when you measure this angle, okay, so this measure is going to be exactly equal to this measure here. See, let's say it's 46 or 50 approximately, right? So if this is 50 degrees, this is also going to be 50 degrees. Clear? So you always have to measure the angles with the normal. This other angle is actually called the glance angle. Okay, the angle made with the mirror. But remember, angles are always measured with the normal. So if this is 50 degree, this is 50 degree. If this is 40, this is 40. If this is 30, this is going to be 30. Angle of incidence is always equal to the angle of reflection here. What is the angle of incidence and reflection in this case? So suppose we have a ray of light which is falling directly on the mirror. So what do I mean by directly? That means perpendicular. So let's say this is 90 degree. Can you guys work out and tell me what will be the angle of incidence and angle of reflection here in this case? So let me remind you again, angle of incidence, angle of reflection is always measured with the normal. So whenever you're talking of angles, first thing you do, don't be lazy, draw the normal. So everybody draw the normal here and the answer will stare back at you. So what is the normal? Normal is going to be again imaginary line drawn perpendicular to the mirror. So will you guys agree? Is this not our normal? N dash. So normal is, the incident ray is actually along the normal. So what is the angle between the incident ray and the normal? And reflected ray will again be, once it hits like this, you know the reflected ray is going to go back like that. Okay. So what is the angle between the incident ray and the normal? We can clearly see angle I is going to be 0 degrees. And by second law of reflection, angle R is also going to be 0. We know if it hits like this, it's going to go back. So the angle between the incident ray and reflected ray is 0. Angle between the incident ray and the normal is 0. And we always measure with the normal, not with the mirror. Glance angle is 90 degree. This angle is actually called angle of glance or glance angle. Okay, that is 90 minus the incident angle or 90 minus the angle of reflection for the reflection case. So here it's going to be both 0 degrees. So now we have done the basics of, what is beam of light, ray of light and all the reflection basics. Now let's look at spherical mirrors and we are going to take a practical example of a spoon. So I would encourage you that after this class, when you guys are having dinner, maybe I also do is I'm going to pick up the spoon and please take a look that when you look at this side of the spoon, the front side and the back side, look at how you look in the spoon. It's actually quite funny, right? So you'll see in some cases you are looking inverted and you can try moving the spoon. So you take the spoon, move it forward, backward and see how you look there. Similarly here, you try inverting the spoon and seeing how you look at behind it, and you can see that the spoon, and take a nice big shiny spoon, right? And spoon is a reflecting surface. Okay, and these are basically curved mirrors. So previously in all the discussion we did, these were all plane mirrors, flat. These are all plane mirrors. Now we are going to the interesting topic of curved mirrors, also known as spherical mirrors. What is the meaning of a sphere? Spherical means sphere, sphere means like a ball. Okay, so what is happening here? But where is the ball here? This is a spoon. Actually the spoon is like part of a sphere. So if you think about it, why is it called a spherical mirror? Because it is part of a larger sphere. So as if this curved surface has been cut off from a sphere. Similarly here, if you take this, as if this curved surface has been cut off from a sphere. Can you guys see that? So that is what we call as a spherical mirror. Now there are two types of spherical mirrors here. That is why spoon is a very interesting example. If you look at this part, right? So when the spoon is curved, like you're going into this cave, right? What is this type of mirror called? When you're looking at the front part of the spoon with which you pick up your food, not the back part. What is this type of mirror known as? What do you guys think? Very good, very good. And the very simple way I remember it is, it's like this hollow curved part where you can enter it, right? As if you're going inside a cave, right? So you're going inside this cave. So this is called the concave mirror. So this reflecting part is called the concave mirror. And if you flip the spoon and you see yourself at the back of the spoon, you can see this is bulging outwards, right? Now you can't enter the cave because it bulges outwards. So it is bulging like this. This is called the convex mirror. So spherical mirrors are categorized into two types, concave and convex. Remember, spherical mirrors are the curved mirrors. They are part of a larger sphere. They are not flat. They have to be curved. So we use our mirrors in our daily lives, right? All the time. So there you can see, and you guys have probably seen this video. If you're not, please watch the other videos also given in the course here. So can you identify what are the different types of mirrors here? So when we comb our hair, this mirror that we're using, what is this type of mirror? First one is definitely a plane mirror. Excellent. How about this one? This is famously known as a shaving mirror. Of course, you can use a plane mirror for a shaving mirror, but normally this one, which is a shaving mirror or a makeup mirror, the advantages, so there you can see I'm, trying to shave here. So the advantage is you see a magnified version of yourself. Okay. You look larger in the mirror. So that makes it very easy to shave because, you can shave carefully and see yourself clearly. And it is also used for makeup or definitely by, makeup artists because it is they see a larger version of the face, right? So this is called a makeup mirror. And what type of mirror is this? Very good. The answer is this is a concave mirror. Concave mirror gives a magnified version. So this answer is going to be concave mirror. And this last one that you see, you have seen this at street intersections or in parking lots. You have seen this kind of mirror. The advantage is it gives a greater field of view because it is curved, bulging outwards. So it gives a greater field of view. You are able to see more and it is curved outwards. This is a convex mirror. So there you can see all these types of mirrors, plane mirror, flat mirror, and these two types of spherical mirror, concave and convex. They are being used all the time in our daily lives, in practical things. And so I would highly encourage you to look around. Whenever you see these types of mirrors, sometimes it may not be obvious because, the curvature is very less. It's slightly curved. For example, in the cars or vehicles, the rear view mirror is only slightly curved. It looks like a plane mirror, but it is actually convex for greater field of view. So I would highly encourage you to look around and, and you can see that in my videos as well. But try to spot what different types of mirrors are being used in your daily lives. Because the more you connect things, the better you'll remember things. So why use these different types of mirrors? The reason is the action is different. What do I mean by that? If you take a parallel beam of light and throw it on a plane mirror, what happens to it? So here you can see there's a parallel beam of light falling on a plane mirror. So after reflection, this beam just reflects off like this. So you can see the parallel beam remains parallel, right? So this it remains parallel even after reflection for a plane mirror. Now if you take a concave mirror, so again remember, this one is a plane mirror, this is a concave mirror, and here you have a convex mirror. So what happens here, if you throw a parallel beam of light on a concave mirror, what's going to happen? These rays will finally meet at a point. So you can see that they will converge to this point. So what this spherical mirror or the concave mirror does is it takes the parallel beam of light and converges it to a single point. What is this point known as? You guys might know about it. Just like the parents say, tell us, right? Focus on your studies, focus on your studies. So here, this is the focus, exactly. Because all the light rays are focused, falling on one point, So this is the focus, and this is basically, you can see that concave mirror has a converging action. It is a converging mirror. Because remember, we talked about light rays, when they meet at a point, we say they converge. So you can see the parallel beam of light after reflection, they are meeting at a single point, which is called the focus. So this mirror is having a converging action. It's a converging mirror. And what about this one? The parallel beam of light, when they fall in a convex mirror. So how do you draw this concave and convex? How do you know the difference? When you draw this curved thing, this dash, dash, dash is basically the back of the mirror. So this is the reflecting part. Same way here, when it is turned like this dashed portion is the back of the mirror. This is the smooth reflecting part. So when parallel rays are falling here, what happens to them? These rays actually end up moving further away. So after reflection, this is what happens to them. When they hit the mirror, they move back further away, they spread out. And if you trace them back,
you can see that they will meet at a point which is also called as a focus, which it's a virtual focus because it's behind the mirror. So this is what a concave mirror, can you see the difference? Here it is converging the beam. Here when the rays of light hit, the beam spreads further. So this is in fact a diverging mirror. So this is a very important slide because it summarizes the difference of action of the three mirrors. We are throwing the same thing, parallel beam of light. This one, after reflection, the parallel beam remains parallel. Here, after reflection in a concave mirror, it converges it to a single point. So it is a converging mirror. This one diverges it away. And if you trace it back, it meets at a point behind the mirror. So convex mirror is diverging. Please remember this because sometimes there's confusion. You know, we mix up these two, or we think this one is converging, this is diverging. So please draw these ray diagrams, and yes, keep your pen and paper ready and make sure you are, when you're drawing it, see I've drawn all the arrows as well for the rays. Very important to do that. Great question by Madhav, that why did I use dotted lines here? Because these rays are real light, right? So these are real rays of light. But when these rays are hitting, this is the real light, this is just imaginary lines. Because they appear to meet, the ray cannot go through the mirror. Why? The mirror is not transparent, it is opaque. So these are basically your, they appear to be coming from this point. Does that make sense? Okay. So one very important thing, because this will come very useful in the next class when we do ray diagrams, how to draw these concave mirror diagrams and convex mirror diagrams. Of course, you can, just draw, you can draw it roughly by just taking a pencil and, just doing an arc like this. But even better thing would be to use a compass. So when you're drawing this mirror, better you use a compass and put, your compass point, let's say over here. So put your compass point here and then draw this curvature using your compass instrument. Okay. So when you put it like this and draw this curved thing, do you guys know what is this point known as? This is called the center of curvature, because it is the center of this big circle or sphere, right? If you think in 3D, it's a sphere. It's the center of this big circle. So that is why it is called center of curvature. So you put the compass at the center and draw this curved arc, right? So don't make it too much curved. It should have a certain, that will come by practice, So have this kind of curvature. This is your center of curvature. And then basically this will be your focus. The focus is exactly at the midpoint of this line and this center of curvature. So what is this line known as? So this is your concave mirror. This line that we draw through the center of curvature, passing to the center of mirror. Very good. This is called the principal axis. And where this thing meets is called the pole of the mirror, right? So that center of the mirror is called the pole. Focus is exactly between the pole and center of curvature. Now, a smart way to draw this is that since you know that this is exactly the midpoint. So for example, if this is, this is 3 centimeters between P and F, C and F is also going to be 3 centimeters, correct? Because focus is exactly at the midpoint of the pole and center of curvature. Focus is that point where the rays will converge for a concave mirror. So what is a smart way to draw this is that you first decide your this is called focal length, or you first decide this distances between these two. You can take any convenient thing, 2 centimeters, 2 centimeters, or 3 centimeters, 3 centimeters. So what you do is using your ruler. So take your ruler like this and measure these distances. Okay. So measure this distance. Let's say it's 3 centimeters on your ruler. So this 0 to 3, this is 3 to 6. So mark these points first. Then you take your compass and then you draw the arc. So that way you're guaranteed that your focus is exactly in the middle. Okay. So this is very, very important. If your focus is not exactly in the middle, your ray diagram will go completely haywire. It will go completely wrong. So this is a very important trick, that rather than starting with the arc, you first measure these distances. Make it convenient. Good question. How big should you do it? Should you make it 40 centimeters? No, it won't fit your page. You can do any convenient thing, 2 centimeters, 2 centimeters, or 3 and 3, or 4 and 4, whatever is convenient for you. But make sure this focus is exactly in the center of P and C. This is called the pole, center of curvature. This is your focus. Okay. So this is how you draw your concave mirror diagram. If you do it like this, you won't go wrong. And then you put your compass point here and then use your compass to draw this arc. And make sure you draw these dashed lines because this represents the back. The non-reflecting side, this smooth side without any dashes is the polished reflecting side of the mirror. And this line which joins P and C and passes through F, of course, is called the principal axis. How big should your arc be? You should draw it a little big so that, you can, as we'll see in the next class, the ray diagrams, the rays will not go outside the mirror because you don't want a ray going outside the mirror. You can obviously extend it. Yeah, if you find 2.5 centimeters the best, you can use it 2, 3, 2.5, but make sure these guys are equal. That's the important thing. Is it necessary to draw the principal axis? Absolutely yes, right? For most of the diagrams, you will see it. So you must draw the principal axis. And we'll see that in the next class, okay? Now we are doing the basics. So make sure you guys practice it the right way, the smart way, okay? So measure these distances, then draw the arc. How do you draw a convex mirror diagram? Same thing, only it is, the opposite side. So because this is the reflecting side, so we tend to, the circle will be drawn this way. Now, once again, this is your principal axis. So your horizontal line, and make sure you're measuring again equal distances. So if let's say this is your pole, your focus, if this is your focus, and this is your center of curvature. So this is my pole, focus, and center of curvature. Again, you can keep, 2 centimeters, 3 centimeters, whatever you want. They basically need to be equal. Your object will be placed here. When you're doing this reflection, so the object is going to be placed here, the rays will go here and reflect off this mirror. And then again, you place your compass point over here and draw this arc, okay? And this time it's a convex mirror. So make sure this back portion has the dashed, okay? So this is the non-reflecting side, right? Just like we draw in a plane mirror. And this side is the reflecting side, the smooth side without any of these dashes or marking. So there you can see this is the convex mirror diagram. Again, focus is exactly between P and C. If this is 2 and this is 2.1, your diagram is going to go wrong. Okay, so measure it very carefully and accurately and use the compass to draw a nice big arc. So there are a lot of light ray rules, right? And again, remember, make sure you draw your diagrams like this. So you have the center of curvature, your focus, pole, which is exactly the center of the mirror. In convex mirror, it is this side. So here it is in front of the mirror because the curvature is this way. So obviously your center of curvature will be this way. Here the center of your compass should lie this because the curvature is this way. So this is your center of curvature and your focus. So there you can see. And so now we're going to talk about light ray rules. So for example, if you have some random ray, like let's say you have this ray, after reflection, where will it go? Or if you have a ray like this, where does this ray go? Or if you have a ray like this going towards the focus, where will this reflect off and go? So there are some standard rules which make it very easy so that we can use these light ray rules to predict where the image will be located. So let's talk about rule number 1. So what does rule number 1 say? And we'll do it together for a concave and a convex mirror. And there you can see these are your P, F, and C, center of curvature, focus, and pole. So if you have your light ray, which is parallel to this principal axis, this is rule number 1, where you can see the ray of light, again, the thin line of light, which is parallel to the principal axis. Where does this ray go? Okay, so what will happen here? This ray, after reflection, the rule is if it is parallel to the principal axis, the ray after reflection passes through the focus. So let's draw that here. After reflection, this ray is going to pass through the focus. There you go. Same thing in a convex mirror. It may look complicated, but same thing. But should you do this? The ray of light parallel to the mirror, it passes through the focus. Is this correct? Is this the right answer? Yes or no? What do you guys think? Have I drawn the correct diagram? See, I did the same thing as concave. I took the ray of light passing to the focus. So I'm happy to know that most of you think this is wrong, because what is the problem here? Mirror looks to be like transparent. The ray of light is going through the mirror. The ray of light is just going through. No, mirror is opaque. So definitely this is wrong. What is going to happen? This ray of light is going to get reflected, bounced back from the mirror, but it will appear to come from the focus. So it appears to come from here and it is reflected off like this. Can you guys see that? So again, parallel ray as if it is coming out from the focus. Here it is actually going through the focus. And make sure this is dotted, because this is like a virtual ray, right? Or it is not real. The real ray of light is here, because it cannot be behind the mirror. So this is your rule number 1. And make sure, please, again, I'll keep repeating, make sure you guys draw those arrows. Arrows are very important. Next, guys, rule number 2. If the ray of light is passing through the center of curvature. So if you take the concave mirror case, this is my center of curvature. This is the focus and pole. If it passes through the center of curvature, what is the rule in a spherical mirror? This thing. So you guys know that when it is passing to the center, this ray of light is like a radius. Do you guys agree? Because this is a big circle. So is it not the radius, the line joining the center to the end of the circle? And we know that this radius is going to be perpendicular to, if I draw this tangent here, do you guys agree? If I draw a tangent over here, using the circle property, we know, or if you guys don't know, you're going to learn that the radius is perpendicular to the tangent drawn at that point. So tangent means what? If I look at this portion of the mirror, this is like a small plane mirror, this tangent mirror, small plane mirror. So if the ray of light is directly falling on this part of the mirror, after reflection, what will happen? Since it is perpendicular, it will simply go back, right? It is falling on the mirror. After reflection, it will simply go back. Because it is normal incidence, it is falling perpendicular. So it will simply go back along its path. So this is one rule which confuses some people. Why is it going straight back? Because this radius of the circle and the tangent, by that theorem, radius and tangent are perpendicular. Tangent means this small part, this actually curved mirror is made up of small tiny mirrors. So if we consider this small part here, this part, this is like a plane mirror. So it is behaving like a plane mirror and just reflecting off the ray back. So that's what's happening here. Similarly, what will happen here? If you take in a convex mirror, you have your pole, focus, center of curvature. All you have to remember, if the ray of light is going through, or it was going towards, not through, it cannot go through it. It is going towards the center of curvature. Same thing will happen. It will simply reflect back. It will trace back along its path. So just like it traces back here, this is going to happen. So these rules make drawing ray diagrams very, very convenient, because these are like the standard rays here. So here we say it retraces the same path. Now let's look at rule number 3. If the ray of light is passing through the focus of the mirror. So there you can see, we'll start off with concave. This is our center of curvature, the pole here, center of the mirror, and focus exactly in the middle. If the ray of light passes through the focus, what will happen to it? This is actually the reverse of rule 1. In rule 1, what happened? Ray of light parallel to the principal axis passes through the focus. Now we are doing the reverse. If ray of light passes through the focus, what will happen to it? It will become parallel to the principal axis. So that's what's going to happen here. The ray of light passing through the focus after hitting the mirror is going to become parallel to the principal axis, right? So after hitting the mirror, this ray is going to become parallel to the principal axis. So basically rule 1 and rule 3 are reverse of each other. Why? Because of reversibility of light. Light will just reverse its path. So if you draw a parallel ray, Does it look parallel? I hope. So if you draw a parallel ray, it will pass through the focus. If you make the ray pass through the focus, it will reflect off and become parallel to the principal axis. Clear? Same thing here. The ray which was targeted towards the focus, which is exactly in the center of curvature and pole, after reflection. Same thing. What's going to happen here? It was meant to go towards the focus. After reflection, it becomes parallel to the principal axis. So just remember, rule 1 is the reverse of rule 3 here. There is one more rule. Rule 4, if the ray of light is falling exactly at the pole, so the point of incidence is the pole. So what is going to happen here? So if you guys see again, remember this center of curvature, the focus here. So line joining pole and center is like our radius. So that is going to be perpendicular to this tangential mirror here. Do you guys agree? So this radius is going to be perpendicular to this tangent kind of mirror here. So this radius is acting like the normal. So therefore, if we use a compass and let's say we measure this angle, and if this angle is 20 degree, this is behaving like a small tiny plane mirror, where this is our normal, PC is the normal, this is our incident ray. So what is going to happen? This ray will reflect off exactly like this, having the same angle of reflection as the angle of incidence. So it's going to be 20 degree again. Can you guys see? Angle of incidence will going to be equal to angle of reflection here. Yes, it will reflect off at the same angle. So the important thing, we are using at the pole, angle I equal to angle R. Same thing for a convex mirror here. It is incident at the pole. This was your focus and center of curvature, of course. And so because this is acting as the radius, the normal here, so again the ray of light will reflect off, making the same angle. So let's say suppose the angle here was 30 degree. This is also going to be 30 degrees here. So this is like our pole rule, where angle of incidence is going to be equal to angle of reflection. But one important thing here, please avoid using this rule in the ray diagrams. Why? Because measuring these angles accurately, like suppose it was 15 degree or 17, then measuring it accurately, even 20, with the compass, the measurements are not that accurate. So the ray diagrams may not be so accurate. But the previous rules never relied on any of the angles. It was just parallel line passing through the pole, through the focus. Here you had passing through center of curvature, gets reflected back, and in the last one, passing through the focus becomes parallel. So these did not use angles. So I would just say avoid using this rule, even though it's valid, avoid it, because angles are very hard to measure. Unless they give you a direct question, okay, they ask you some question based on this diagram, then you should do it. But for ray diagrams, this rule is to be avoided for ray diagrams. And we are going to practice the ray diagrams in the next class. So make sure you revise this, watch the previous videos before attending the next class. Now, one very interesting thing is random ray. If we have this kind of random ray, so you can see it is not following any of the rules. Is this ray parallel to the principal axis? So here you have your pole, focus, and center of curvature. These are pole, focus, and center of curvature. So is this ray parallel? No. So we cannot use rule 1. Is it passing through center of curvature? No, we cannot use rule 2. Is it passing through the focus? No, we can't use rule 3. Is it incident at the pole? No, we can't use rule 4. So I like to call this the random ray. Okay. So what do we do in this case? We know that when it is hitting the mirror, where do you guys expect this? This ray is not going to go here because it is not transparent. So that is wrong. So if this is kind of a curved mirror, I'm expecting it's going to come something like this. Right? It's going to reflect off like this. Do you guys agree? Okay. But how do we draw it accurately? Roughly, this looks correct. Okay, it's hitting here. It should go somewhere here. But is it going to focus? Where will it go? So how do we do some more accurate estimate of where this ray is going to go? So again, there, what we are going to do is we are going to use the idea that if at this point of incidence, this is my point of incidence, O. So if I join All you have to do is join O and C. Just join the point of incidence and the center of curvature, because this is like the radius of the circle. So it is definitely going to become again the normal to this small plane mirror here. This is like a small tiny plane mirror, because circle is made up of small tiny lines. So you can see that this is basically going to become the normal to this incident ray. So after reflection, you guys can guess it is going to go like this, where what you can do is to measure it accurately. Suppose this angle was 25 degrees, then this angle will also be 25 degrees. Do you guys agree? It looks a little larger than that. So maybe let's say I say this is, or let's just say this is 30-degree angle or 40 degrees. Okay. So what you can do is you just join O and C, you measure this angle 40 degree, this angle here equal, and you will get your reflected ray perfectly, because OC, the important point is OC is the normal. The line joining the point of incidence to the center of curvature forms the normal. You measure this angle of the incident ray with the normal, you draw that equal angle, and boom, you're done. So yes, it passes somewhere between P and F. Same way, what will be the random ray rule over here? Follow the same procedure. Look at the point of incidence. So this is clearly my point of incidence over here, which I can label as O. And this is my pole here, the focus and center of curvature. Again, what is the rule? Join OC first, okay? Make your normal. So we are going to join O and C and extend the line like this. Now, once again, measure this angle. So suppose this angle turns out to be 30 degrees. You draw the same angle here, because you know after reflection it's going to angle I will equal to angle R. So this is going to be same angle here. So do spherical mirrors obey the laws of reflection? Does angle of incidence equal to angle of reflection? The answer is yes, as you can see here, because a spherical mirror is made up of tiny small parts or tiny plane mirrors. So definitely it is following the laws of reflection. You just have to draw that normal OC, you join that, and there you can see angle of incidence equal to angle of reflection, and there you're done. And another important thing you guys need to know, which will be useful in the next class, what are the types of images? So images can be divided into two types: real image, virtual image. We'll see this more in the next class. The important thing is real image can be taken on a screen. So just like when you go to the theater to watch a movie, they are projecting on a screen, so it can be captured on a screen. It is a real image. Real images are always inverted upside down. Why don't you see the inverted image in the movie? Because they invert the projected thing, right? And light rays actually meet at the point. So real means the light rays are actually meeting to produce the image. Whereas virtual image, it cannot be taken on a screen. So real image on a screen, virtual cannot be taken. Real image is always upright, or we say erect. These guys are upside down, inverted. Inverted means upside down. And light rays appear to meet. So in virtual image, the light rays don't actually meet. They seem to be coming from a point. So we'll see that. So this is an important thing you should remember for the next class. Let's first look at the light ray rules for spherical mirrors. Remember, there are two types of spherical mirror: concave mirror and convex mirror. So what do you think this mirror is? That's right, this is a concave mirror, because it's like entering a cave. You can see this is the back reflecting portion, and this is a convex mirror. It is bulging outwards. So this is where the light ray falls. And concave mirror, remember, is a converging mirror. This is a diverging mirror. And then you have these important points of the mirror, which is the pole is the center of the mirror, C is the center of curvature, center of the circle or the sphere. And please remember to mark the focus exactly between P and C. So if this is 3 centimeters, this should be 3 centimeters. If this is 2 centimeters, this is 2 centimeters. So remember, focus should lie exactly between P and C. And what is this line joining P, F and C? That's right, it is called the principal axis. Similarly, here if you look, this is a convex mirror. So this is pole is exactly the center of the mirror. C is the center of curvature. So if you join the, it's part of this circle, and focus again is lying exactly between P and C.
So make sure you guys draw these diagrams as we had discussed very carefully. Draw the spherical mirrors using a compass and make sure your focus is exactly between P and C, and you join this line which is called the principal axis. Now let's take a look at the light ray rules. For example, if a ray of light is falling on the mirror, how do we predict where it will go? And this is very important because we are going to use the light ray rules to predict the position of the image when an object is placed in front of these spherical mirrors. So let's take a look at the light ray rules. So here's first the rule number 1, where we are going to do together for a concave and convex mirror. So to make it easy for you guys and you'll remember it better, and we are going to start with rule 1, where the ray of light is parallel to the principal axis. Can you see? It's drawn parallel to the principal axis. And this is the pole, center of the mirror. This is center of curvature. Focus is exactly between P and C. And similarly here for a convex mirror. P, F and C. So now where does this ray go? If the ray is drawn parallel to the principal axis, rule 1 says that after reflection for a concave mirror, it is going to pass through the focus, because this mirror converges the light rays through the focus. So please draw that right now. The ray of light parallel to the principal axis after reflection passes through the focus of the concave mirror. Now in a convex mirror, what will happen? The ray of light which is parallel to the principal axis after reflection, will it go like this, passing through the focus? Is this correct? No, because the mirror is not transparent. Light cannot go through it. Mirror is opaque. It is a reflecting surface. So the light is going to reflect off as if it was coming from the focus like this. So there you can see the light seems to be coming from the focus, and this is for a convex mirror. So there you can see the difference. Here the light is actually reflecting and passing through the focus, which is why this is a real focus. Here the focus is virtual because it appears to come from the focus. So this was rule 1. Now let's look at rule 2. Rule 2 is a very interesting rule where the ray of light is passing through the center of curvature of the mirror. So there you guys can see that it is passing through the center of curvature C, or here it is going towards the center of curvature for a convex mirror. For a concave mirror, it actually goes through the center of curvature. So this is a very interesting rule because very simple, that when the ray of light passes through the center of curvature, it will simply reflect and retrace its path. So the ray of light is just going to go back like this, just retracing the same path. Same thing for a convex mirror. When it is appearing to come towards the center of curvature, after reflection, it just retraces the path. That's it. Now why is this happening? Why is it retracing the path? This is very interesting because remember circle, there's a theorem that if you join the center to the perimeter of the circle, what are you drawing? Radius. And if I look at just this part of the mirror, a curved mirror is made up of small tiny plane mirrors. So this part is like a tangent. So I'm drawing a tangent to this circle. This is like a tangent here. And we know that the radius is going to be perpendicular to the tangent. Radius is always perpendicular to the tangent. That is why you can see that this ray of light is acting like a normal. When you have normal incidence, angle of incidence is 0. Angle of reflection will be 0, because when you have light incident normally, it will simply retrace its path. Same thing over here, that if you look at this, if you draw a tangent, this small plane mirror here, then it is perpendicular to the radius. Once again we are having normal incidence, so it is simply going to retrace its path. So this was rule 2 for concave and convex mirrors. Rule number 3, what is the third rule? Third rule is when ray of light is passing through the focus for a concave or appearing to go towards the focus, because again it can't go straight through. Mirror is opaque, it is not transparent. So let's say here the ray of light is passing through the focus here of the concave mirror or going towards the focus here. So now what's going to happen? So this is like the reverse of rule 1, because remember in rule 1, ray of light parallel to the mirror or parallel to the principal axis of the mirror passes through the focus. So what if I retrace, I reverse the light? If I make the light go through the focus, what will happen? It will become parallel to the principal axis.
Because remember, the path light is reversible. It's called reversibility of light. If light goes this way of a reflection, it will retrace back the same path. So rule 1, if you turn it around, it becomes rule 3. That light going through the focus will become parallel to the principal axis. As simple as that. So what's going to happen here? Ray of light passing through the focus after reflection becomes parallel to the principal axis. So this is what's going to happen. There you go. So after reflection, it becomes parallel to the principal axis. Similarly here, ray of light passing through the focus after reflection is going to become parallel to the principal axis. There's our answer. Clear? So you can clearly see rule 1 and rule 3 are reverse of each other. Rule number 4. What is rule number 4? If ray of light is directed to the pole which means it's exactly the center of this curved part, the spherical mirror. So if it is directed towards the pole of the concave mirror or the pole of the convex mirror, what will happen to this ray of light? So now we learned that if it is hitting the pole, then once again this principal axis is acting as a normal because it is passing from center of curvature to the point of incidence. So now it will follow like a normal law of reflection. The ray of light will be reflected like this, where angle of incidence will equal to angle of reflection. So let's say this angle is 20 degrees here. After reflection, the angle will be 20 degrees. So it will follow like it looks almost like a plane mirror diagram, where because basically spherical mirror follows all the laws of reflection, and in this special case the principal axis is acting as a normal. So there you can see if angle of incidence is 20 degree, angle of reflection is also 20 degree. So here you can see angle I is equal to angle R is 20 degree. Clear? Can it be 0 degree? Well, then it will become rule 2. If the ray of light is passing through the center of curvature, obviously it will bounce back. So there you can see this is the rule. And similarly for a convex mirror also, let's say this angle is 30 degree. So it will bounce back off the mirror, making the same angle of reflection as the angle of incidence. Important thing to realize is why are these angle of incidence and reflection here? Because this is our normal. It is perpendicular to the point of incidence, the line passing through the center of curvature, which is the principal axis here. Once again here. So there again you can see angle of incidence is equal to angle of reflection is equal to 30 degree. This is rule number 4. Now one very, very important point here, that when drawing ray diagrams, which rule should we use? Do we have to use all the rules or only some of them? So that is one very important thing, that which you have seen in plane mirrors also. To produce the image of an object, what is the minimum number of rays that you guys need? Can you guys tell me? If you want to form an image of an object, what is the minimum number of rays that you need? Very good. The correct answer is 2 rays, because if you just have 1 ray, you're just getting the light path, but object is usually, having a certain height or length, right? So you need 2 rays, right? And you need the 2 rays, and we usually take it from the top of the object and see where they intersect to form the image. So like you have seen in my videos, the minimum number of rays that you need to form the image is 2. So therefore, how many rules do I need to use? Only 2 out of these 4 rules. You don't need to use all the 4. So we need to use only 2 out of 4, but which one should we use? I would recommend to use rule 1, 2 and 3. Do not use rule 4 unless it is necessary or you get some direct question like here, because this relies on measurement of angles. To draw the reflected ray, you have to measure these angles very accurately, because if this is 20 degree, you have to measure with the protractor 20 degree accurately and draw the ray, and measurement with the protractors are never super accurate. Okay, so please avoid using rule 4. So I'll write this important note here: avoid using rule 4. So that's something very important for you to remember. And then of course I have this random ray rule, where basically I'm just saying that if you given some random ray like this, which does not pass through, it's not parallel to the principal axis, doesn't pass through pole or center of curvature or focus, then what do you guys do? How do you draw where will this ray go? Then the interesting thing is that now, since this is a curved mirror and it follows
laws of reflection. So we really have to measure the angle of incidence and then draw the reflected ray according to that. But how do we measure the angle of incidence? Remember, the angle of incidence is always measured with respect to the normal. So the question is, where is the normal here? This is your light ray. To use that angle I equal to angle R, you need the normal. How do you get the normal? Very simple. Just join the point of incidence, let's say this is the point of incidence, to the center of curvature. So very good. That is the only thing you have to remember, that if I join the point of incidence and the center of curvature, let's call the point of incidence O here. So if you join OC, you have basically drawn your normal. Why? Because this is like the radius. So once again, you know, it's perpendicular to the tangent drawn over here. So this is my normal, and now you can easily draw the reflected ray. So first you measure the angle of incidence. Let's say this angle turns out to be 30 degrees. So now you draw the reflected ray, which makes an angle of 30 degrees with the normal. Done. So this is not really a rule. This is, I should say, random rule technique. Okay. So maybe we can call this random ray. It's more like a technique here. And the whole technique relies on drawing that normal. After that, now you have to measure the angles here with the protractor. So you can't do anything. But typically, you will not use this kind of stuff. You will only use 2 out of the first 3 rules. And same thing here. For a convex mirror, what will you do? Same thing, that you are basically going to draw the normal here, right? So that's what you're going to do. Yes. So once again, you have your pole, you have your focus and center of curvature. This O is the point of incidence. So go ahead and join O and C to form your normal, and just extend OC. There you go. So what is this angle? Let's say this angle now is whatever 30 degree or whatever angle you're getting here. And then after reflection, this is going to make the same angle of reflection here. So there again, same, join the normal, angle of incidence equal to angle of reflection, and you're done. So now let's come to our important thing. Again, please make sure you guys watch the other videos in this chapter. So how to find the image? Because in a plane mirror, it is very simple, right? If instead of a curved mirror, you just have a plane mirror, then we know object distance equals image distance, and you can actually cheat and, you know, plot the, and object height is same as image height, so you can easily get the image here. But here it is not the case, right? You cannot say object distance equals image distance, object height equals image height. Will this be correct? No. So that is why to predict the image here, we need to use the light ray rules. And as I said, 2 out of the first 3 rule. Avoid using that pole rule, and random rule was just a technique. Because sometimes, you know, they may say complete. So why did I teach this thing? Because sometimes they say complete the ray diagram. So you have to use this technique of joining OC and drawing the diagram. So let's go ahead and try it out, guys. So let's say you have an object like this, and let's mark the object as AB. And once again, like we discussed in the previous class, make sure you're drawing this with a compass and your focus is exactly between P and C. So if this is 3 centimeter, this is 3 centimeter. Make sure you guys do that. So let's mark the center of curvature, the focus, the pole here. Okay. And make sure these are equidistant. So if this is 3 centimeter, this is 3 centimeter. Now, to find the image, remember we have to draw the rays. And the important thing is draw the rays only from the top of the object. What will happen to the base or the bottom of the object, I'll show you, but please draw the rays only from the top of the object, which we can call as A. So we need to draw 2 rays to determine the image of A this side. So which rule do you want to go for? One of the simplest rule is rule 1, where you can draw a ray parallel to the principal axis. After reflection, it will pass through the focus. So let's do that. So ray of light parallel to the principal axis. And we know this concave mirror is converging mirror. The focus lies here, right, on the left hand side. So it's going to pass through the focus. So see, after reflection. So there you can see that's how the ray will go. After reflection, it will pass through the focus. So we have used rule 1 over here. What other rule should I use here? So either you can have the ray going through the center of curvature and it will bounce back over here. So you can do that. Or you can have a ray passing through the focus and then parallel. So again, you can use any two which are convenient. Don't be confused that I have to use the first 2 or, you know, first and third. any two rules that are convenient for you. So maybe here we can have the ray of light passing through the focus. So something like this. And if the ray of light passing through the focus, it will become parallel to the principal axis. So we can draw it something like this, parallel to the principal axis. So after reflection, that's where the ray will go. So good question. You guys should draw both the rays from the top of the object, not from the bottom, right? So there you can see, and here the object is kept beyond the center of curvature. So where are we finally getting our image? So this is the top of the object A. So the point where these rays intersect, what do you think is this point? Is it the top of the object or the base of the object? Since the rays are coming from the top of the object, this better be the top of the object, not the base. So let's mark that as A dash. And where will the base lie? So if I want to draw the image, so this top of the object, this is the top of the image, A dash, right? And why have I marked A dash? Because it is the image, it's not the object. And now where will the base lie? It's very simple. You just have to join this to the principal axis. So this point A dash is the top of the image and this is B dash, the base of the image. Done. So can you guys see? We have got our image here for a concave mirror where we use rule 1 and rule 3. As simple as that. If you use rule 2, you would also get the same thing. Of course, my diagram is a bit rough here, but you will have the same ray passing through the center of curvature and it will again give you the image at A dash. Now, one very important thing when you guys draw the ray diagram, it is also important to write the properties of the image. So, can you guys tell me what are the properties of the image here? So, clearly the image is inverted, and can you see that the image is a real image because it is formed due to the real intersection of rays? Do you guys agree? So, this is clearly a real and inverted image because the rays are really meeting to form this image. What other thing we can see here? The second property we can say is the image larger, smaller or same size? So if you look carefully, you can clearly see object AB is larger than our image A dash B dash, and please remember to label it, right? A dash B dash, okay? Try not to draw the image as dotted. Sometimes it's shown as dotted. I like to draw it as a solid, right? Just mark it as A dash B dash. So you can clearly see it is smaller. So we say smaller means diminished. So it's smaller in size. We can see it is a diminished image. And the final property is what is the position of the image. So when the object is kept beyond the center of curvature, you can see image is formed between focus and center of curvature. So we can say it is formed between focus and the center of curvature. So that's where we can see the image is produced. Is it important to write the properties? Typically yes. If your school teacher says no, it's fine just to show the diagram. Usually the teachers also like to write the properties of the image formed. You don't have to draw the rays from the base of the image object, because if you just draw this ray, it is going to bounce back and go here. That is why the base is formed here, right? So do not show or draw the rays from the base. Just drawing it from the top of the object is enough. So that's why we said that, there are different types of images, real images, virtual images. So make sure you guys write the property as we had discussed last time. Real images can be taken on a screen and real images are always inverted and the light rays actually meet. So like we saw in the diagram here, so this is clearly real image and it is inverted and the light rays are actually meeting to form our image. It is not being produced backwards. Whereas in a virtual image, it cannot be taken on a screen. It is upright. That means it is erect and light rays appear to meet. They do not actually meet. Let's try another concave mirror question. This time we have moved the object beyond center of curvature. This time the object is placed between the pole and the focus. So now can you guys draw the ray diagram and try to predict where the image will be formed? Of course, you can learn the different cases and learn what do you expect to see here. But first let's practice these ray diagrams. So again, remember you need only two rules and draw the rays from the top of the object. Use only two out of the first three rules. So let's try it out, whichever one is convenient for you. So here you can see this is our center of curvature, this is the pole, and focus is exactly between P and C. So when we draw the rays, what does it look like? Again, we can go for the simple ray, which is a ray parallel to the principal axis will pass through the focus after reflection. So let's do that. Ray parallel to the principal axis, after reflection, it passes through the focus.
So there, I've used rule number 1. What else can I use, guys? Rule 2 or rule 3, what do you guys suggest here? So rule 3 looks a little strange because, I can't have the ray passing through the focus, it's going outside the mirror. So maybe I can try rule 2. So for rule 2, what we can do is, again the ray is not passing through center of curvature, but maybe I could take a ray which is coming through the center of curvature, right? As if appearing to come from there. So if we had a ray like this, we know that after reflection it will bounce back. Do you guys agree? So ray which is targeted towards the center of curvature simply bounces back here. So after reflection the ray will become like this. Does this make sense? So great question. We are tempted to use rule 4 over here. We are tempted to do that. But what did I say? Avoid rule 4 because it means measuring angles, drawing angle of incidence equal to angle of reflection, and there are chances of errors there. With the protractor you have chances of errors. So please avoid using rule 4. Only use it if it's a direct question or if you run out of ideas. But no, you should not be using rule 4 because protractor measurements are inaccurate, so your diagram can go inaccurate. Okay, so what is happening over here? In this concave mirror, you can see these are the two rays of light, and again I know it's not looking like a perfect diagram, so let me just improve this ray here. Hopefully that looks better now. So what you can see here, these rays are moving further apart, right? So they are diverging. So where will the image be formed if the rays are diverging out like this? So now I need to trace them back. So let's produce them backwards. So this ray will go like this, and this ray will produce backwards, and maybe they'll meet somewhere over here. Let's say they meet at this point. So very good, the image is going to be formed behind the mirror because here they are not converging, they are diverging. The reflected rays are moving away, right? So they will finally go ahead and meet over there. So now if this is our object AB, where is our image formed? Behind the mirror, A dash, B dash. Remember I said where the rays meet, that is the top of the object A dash, you just draw a straight line to the base and there you have your B dash. Okay, so now what are the properties of this image? Can you guys tell me? Again, you can learn the properties or you can just, easier is observe it from the diagram. If you have drawn the diagram, you just follow your diagram and write down the properties, because you can't draw a diagram and write some different properties. You can't say this is inverted. You can see the image is erect here. So let's write down the properties here. So image properties. So first image property is, it is clearly, is it real or virtual? It is clearly virtual and upright. It is not inverted. So first property you should decide real or virtual. It is virtual and upright or virtual and erect. And clearly it is virtual because it is formed by producing the ray backwards. They are not actually meeting. We have made them meet. It's behind the mirror. So clearly virtual image. Second point, is it size, right? Is it same size? Is it diminished, magnified? So clearly you can see this image is magnified, much enlarged, right? So clearly we know that the image is magnified, it is enlarged. And what about the location? So you don't have to write anything related to P, F and C. You can just say it is formed behind the mirror. So image is formed behind the mirror, as you can see here. Again, let's try this question where the object is exactly at the center of curvature for a concave mirror. So can you guys see? It is exactly at our center of curvature of this mirror. And again, to get it accurate, make sure these distances are equal, right? If this is 3 centimeters, this also should be 3 centimeters. So how do you do this one? So one, of course, we can again use our rules. So we can go for, so in the ray diagram, if you use your ray parallel to the principal axis, it will pass through the focus. Again, ray passing through the focus will become parallel to the principal axis. And you can see the image, my image at least, is formed somewhere here. Is this the correct answer? So I used all the rays correctly and I got to this answer. But if you do this in the exam, even though you used all the correct rules, you will get it wrong. Why? Because this one is a very tricky one. Even if you try to draw the diagram very accurately, small errors will happen, because we know there's actually a cheating trick here. We know that if it's a concave mirror and the object is placed at the center of curvature, where will the image be formed? Exactly at the center of curvature, and it will be the same size.
So you can first cheat here, draw your image and then you draw the rays. Okay, don't tell the secret. Okay, so first, but all teachers teach the secret, so now it's no longer a secret. Make sure you guys draw the image first, same size, so measure the same height as the object, draw it at the center of curvature, then you draw your rays. So that way you'll never go wrong. Okay, so I'm going to erase all of this. This is all wrong, and let's restart now with the cheating technique. So I'm actually cheating doesn't mean you're cheating from your friend, right? Don't do all that. This is your smart technique. So the smart trick here. So first draw the image same size as the object. So this is our object here. Let's say this is length 3 centimeters. So please draw the image exactly at center of curvature with the same length. Now please draw your rays. So you know that if you draw the ray parallel to the principal axis, after reflection it's going to meet here. So now you can join these guys. So that's my ray, and then ray passing through the focus. After reflection we know it's going to go through this point again. So there maybe again I have to do some cheating tricks there to make it match. Again I'm drawing a freehand diagram on the digital board. For you it will be much easier when you do it on pen and paper. But this is the trick, that make sure your image is same as the object size and it's at the center of curvature, and there you get the diagram. And clearly here you can see image properties are going to be real and inverted. It's going to be same size as the object, and then we know it's going to be formed exactly at the center of curvature. So those are the properties. So decide real, virtual and inverted upright, right? What is the size and then the position of the image. Let's try a convex mirror. So we have been doing concave mirrors till now. Convex mirror, let's try. So let's say the object is kept here in front of the mirror, and this is our pole, focus and center of curvature. So again we are going to use the rays from the top of the object. So this is our object AB. So first let's start off with the ray parallel to the principal axis. So after reflection we know it's going to pass through the focus, or rather it appears to pass, right? Because it cannot go through this way. So we trace it back like this. So this is our reflected ray. And then let's say we have another ray which was aimed towards the center of curvature, but after reflection it will go back. So it will retrace its path. So there you go. So where the two rays meet, that is our top of the object. So where is the top of the object? Because they're reflected off this way, they are meeting actually behind the mirror. So here you guys can see this is going to be the top of the, not object, top of the image. So our image is going to be something like this, A dash, B dash. Okay. So can you guys see? The image is formed not at infinity, it's formed behind the mirror because it's a virtual image. Of course, because these rays are diverging. So we produce the reflected rays backward and it meets behind the mirror. So what are going to be the properties of this image? Always first question, real or virtual, and similarly erect or inverted. Clearly you can see it's a virtual image formed by retracing, and obviously it is upright also. So virtual and upright, or virtual and erect. Similarly, is it magnified or diminished? We know convex mirror always forms diminished, and as you can see it is smaller in size. And how about the position? You can simply say between P and F, or you can say behind the mirror. So here, since it's located between P and F, let's write that down. So between P and F and behind the mirror, there you can see. So please remember to use these things, right, to write the properties like we discussed, real, virtual image. So always ask yourself when you're writing the properties, is it real or virtual? Similarly, real images are always inverted, virtual are always upright or erect. Next, you should write that what is the size, same size, diminished, magnified. Magnified means larger. And last is the position of the image. So make sure you write these properties for every image. Here I am on the principal axis of a concave mirror. Can you predict where my image will be formed and the properties of the image? One method is to use the light ray rules and draw a ray diagram like this. As you can see, this is the position of my image, and it's a real, inverted and diminished image. I discussed this method of image formation using ray diagrams in an earlier video. If you haven't watched that video, Do check it out. In the video, I'm the object and we try to find the position and nature of the image using the light ray rules. In this video, we are going to learn a completely different approach. We are going to look at sign convention and some formulae for mirrors that will help us predict the nature and position of the image. We'll see how to apply these formula by looking at some examples. Remember, there are two types of spherical mirrors, concave mirror and convex mirror. The two methods that we talked about, ray diagrams and formulae, will give us the same answer for the nature and position of the image. But the formula method is more powerful because if two things are known, you can easily calculate the third unknown using the formula. For example, if the object position and focal length are given, then we can find the image position. Or if we know the object and image position, we can easily calculate the focal length of the mirror. In this video, our focus is going to be on this formula approach. But before we look at the formulae, we need to know the sign convention for spherical mirrors. According to the sign convention, the object and image distances, the object and image heights, and the focal length of the mirror, they all have a sign, positive or negative. The sign is decided by the sign convention. Let me show you a very simple way to understand the sign convention. Imagine we are placing the coordinate axis, the x and y axis, with the origin at the pole of the mirror. And the x axis is along the principal axis, as shown here. In this example, we are using a concave mirror. Hold on. Let me go ahead and stand on the principal axis and show you the sign convention. Here I am at the pole of the mirror and at the origin of the x and y axis. According to the sign convention, the object is always placed on the left hand side of the mirror. So light from the object is coming from the left hand side. All distances parallel to the principal axis are measured from the pole of the mirror. Distances that are measured to the right of the origin, that is along the positive x-axis, are considered to be positive. And distances measured to the left of the origin, that is along the negative x-axis, are considered to be negative. Distances measured perpendicular and above the principal axis, that is along the positive y-axis, are considered to be positive. And distances measured perpendicular and below the principal axis, that is along the negative y-axis, are considered to be negative. Similarly, for the convex mirror, imagine you are placing the coordinate axis, the x and y axis, with the origin at the pole of the convex mirror. And the x axis is along the principal axis as shown here. Once again, when we measure the distances and heights, they have a sign according to the sign convention. Let's place the sign convention for concave and convex mirrors on our concept board. Now let's take a look at the formulae for concave and convex mirrors. The first formula is called the mirror formula. 1 by V plus 1 by U equals 1 by F. Here V is the image distance. Remember, the distances are measured from the pole of the mirror. So V, the image distance, is the distance from the pole to the image. U, the object distance, is the distance from the pole to the object. And F here is the focal length of the mirror. So it's the distance from the pole to the focus of the mirror. These distances have a sign, positive or negative, based on the sign convention. Let's go ahead and take a look at an example. Let's say the object is placed 15 centimeters in front of this concave mirror. Since the distance is measured from the pole and it's along the negative x-axis, so u equals minus 15 centimeters. Typically, the object distance will always be negative since the object is placed on the left side of the mirror. Let's say that the focal length is 10 centimeters. The focal length is the distance from the pole to the focus. Since the focus is in front of the mirror, the focal length is along the negative x-axis. So f equals minus 10 centimeters. Now we want to find the image distance v. What sign should we take for v? Positive or negative? That's right, we don't take the sign. Since v is unknown here, we don't write the sign for it. We will automatically get the sign once we solve for v using the formula. To find the image distance v, let's apply the first formula, the mirror formula. 1 by v plus 1 by u equals 1 by f. Let's substitute the values with their correct sign. On solving, we get v equal to minus 30 centimeters. This means that the image is 30 centimeters from the pole of the mirror and along the negative x-axis. So it's a real image since it is formed in front of the mirror. The second formula is regarding magnification. Magnification m is defined as image height by the object height. In symbol form, it's usually written as m equal to h dash by h, where h dash is the image height and h is the object height. Or in some textbooks, you might find it as m equal to I by o. Once again, I is the image height and o here is the object height. Now let's understand magnification with the help of a simple example. Let's say I am standing in front of a concave mirror. Here I am the object and let's say my height on your screen is 4 centimeters. Since my height is measured from the principal axis and it's along the positive y-axis, so my height or the object height is going to be plus 4 centimeters. Now my image here is magnified and it has a height of 8 centimeters. Once again, the image is along the positive y-axis. So the image height is plus 8 centimeters. Now what's the magnification here? Remember the formula? M equals image height by object height. So if you substitute the numbers, we get m as 2. And this makes sense because the image is 2 times the object height. The image is double of the object here. Now if I stand in front of a convex mirror, remember a convex mirror always gives a diminished image. So let's say my image in the convex mirror is half of my height. The object height here and the image height are both positive because they are measured along the positive y-axis. So what's the magnification here? That's right, the magnification is half. And the number makes sense because the image is half of the object height. Now let us look at a case where the image is inverted in a concave mirror. So what's the magnification here? Let's use the magnification formula m equal to image height divided by the object height. Now the image height here is minus 8 centimeters because the image is along the negative y-axis. And the object height is plus 4 centimeters because I am the object and my height is measured along the positive y-axis. So the magnification is minus 2. Now the negative sign tells us that the image is inverted. and 2 tells us that the image height is double of the object height. The third formula relates magnification to the image and object distance. Magnification m is the negative of image distance divided by the object distance. We can write it as m equal to minus v by u. Now if we combine the second and the third formula, we get a fourth formula. H dash by h equals minus v by u. So we have a total of 4 formulae for our spherical mirrors. Let's place the 4 formulae for spherical mirrors on our concept board. Now let's take a look at some examples of how to apply the sign convention and formulae for mirrors. Let's start with our first example. Find the position, nature and size of the image when an object of size 1 centimeter is placed at a distance of 9 centimeters from a concave mirror of focal length 6 centimeter. First, you should draw a rough diagram of a concave mirror and an object placed in front of the mirror. Next, draw the x and y axis for the sign convention. Now let's write the data given to us. Object distance u equals 9 centimeters. We also need to consider the sign. What is the sign here? Since the object is on the negative x-axis, u is equal to minus 9 centimeters. Now what should we write as the focal length f of the concave mirror? Plus 6 centimeters or minus 6 centimeters? That's right, f is equal to minus 6 centimeters. Since the object is along the positive y-axis, object height h is equal to plus 1 centimeter. We need to find the image distance and the image height. Since these are unknown to us, we don't have to worry about their sign. To find the image distance, let's write the mirror formula. 1 by v plus 1 by u equal to 1 by f. Substituting the values and solving, we get the image distance v equal to minus 18 centimeters. So the image is formed on the negative x-axis, that is in front of the mirror and at a distance of 18 centimeters from the mirror. To find the nature and size of the image, we need to find the magnification. Let's use the magnification formula m equal to minus v by u. Substituting the image and object distances with their sign, we get m as minus 2. To find the image height, let's use the other formula for magnification. M equal to h dash by h, where h dash is the image height and h is the object height. Substituting m and h, we get image height h dash equal to minus 2 centimeters. So the image height is 2 centimeters and the minus sign tells us that the image is inverted. So the image is real and inverted and the image size is 2 centimeters. Now let's try a convex mirror question. An object of height 5 centimeters is placed at a distance of 10 centimeters from a convex mirror, which produces a virtual image of height 3 centimeters. Find the focal length of the mirror and the position of the image. Again, the first thing you should do is draw a rough diagram of a convex mirror and an object placed in front of the mirror. Next, draw the x and y axis for the sign convention. Now let's write the data given to us. What should I write for the object distance u? Plus 10 centimeters or minus 10 centimeters? You are right, u equals minus 10 centimeters. The object height h equals plus 5 centimeters, since the object is along the positive y-axis. A virtual image of height 3 centimeters is produced. So will the image height h dash be plus 3 centimeters or minus 3 centimeters? That's right, h dash equals plus 3 centimeters. Remember, A virtual image is always upright. It is erect. The upright image is along the positive y-axis. So the image height will be positive. First, let's find the magnification m using the object and image heights. M equals image height h dash divided by the object height h. Substituting the values, we get magnification as 3 by 5, which is equal to 0.6. Now let's use the other magnification formula, m equal to minus v by u, to find the image distance. Substituting the magnification and object distance values, we get the image distance v equal to plus 6 centimeters. The image is along the positive x-axis. So the image is formed 6 centimeters behind the convex mirror. We know the object distance and image distance. Now we can easily calculate the focal length using the mirror formula. 1 by f equal to 1 by v plus 1 by u. Substituting the values and solving, we get f equal to plus 15 centimeters. The focal length of a convex mirror is positive, since the focus lies behind the mirror on the positive x-axis. I hope the concept of sign convention and formulae for spherical mirrors is crystal clear to you now. Friends, the best way to revise this topic is to practice more sums. We are going to look at mirror formula sums. So this is a very important topic in this chapter, where last time we had done looked at how to predict the image, draw the image using the ray diagrams, using the rules for the different rays, like rule 1, rule 2, rule 3 for the spherical mirrors. But today's class is going to be very different, because we are going to use the formula approach, which is the mirror formula, and we'll be looking at these, doing a quick recap of these formulas and see how to apply them. And I'm going to make it super easy for you, but this is a very important topic because always sums come based on these mirror formulas. So make sure you guys keep your pen and paper ready, and let's practice this together. And also please watch our previous videos on this. So please watch the video for the details, but I'm going to do a recap on the spherical mirror formulas. What do we mean by spherical mirrors? Spherical mirrors means curved mirrors. There are two types of spherical mirrors, concave and convex mirrors. And these formulas can be used to predict, if you place an object, at a certain distance with in front of a spherical mirror, concave or convex, with a certain focal length. Using these formulas, we can predict where the image will be formed without drawing the rays diagram. It's important to draw a rough diagram to visualize, which I'll show you, but you don't have to draw all the rays. You can just predict it using this formula, or what will be the magnification, we can find that out. Okay, so what do these formulas mean? The first formula, r equal to 2f. What does this capital R stand for? Capital R is the radius of curvature. Right? Radius of curvature means spherical mirror is a curved mirror. So what is that radius of curvature? That means the distance from the center of curvature to the pole. That is basically twice the focal length, because we know that focus is halfway. Right? It is exactly at the midpoint of the pole and the center of curvature. So if you look at the principal axis, for let's say a concave mirror, then you have the pole, the focus and the center of curvature. Radius of curvature means P to C, this distance. And this is the focal length, distance from pole to focus. And what is the relation? R equals twice the focal length, because you can see that focus is exactly in the midpoint. Like I told you, if this is 3 centimeters, this should be 3 centimeters. So total radius of curvature is 6 centimeters and focus is exactly in the middle. Next formula, so that is the simple relation, r equal to 2f, or focal length is half the radius of curvature. Now what is the next formula? This is very important, 1 by f equal to 1 by v plus 1 by u. So it's very important to understand what are these terms. U and V is not initial velocity, final velocity. What do they mean here? So in this chapter they mean different things, right? In Newton's laws of motion or equations of motion, this is our initial and final velocity. So what do we have here? Here F stands for, F is the focal length, what does U stand for? U is the object distance, and V is the image distance. Now all these distances, where are they measured from? One very important thing, they are always measured from the pole, which is the center of the mirror. So focal length, just like distance from pole to focus. Object distance, distance from pole to the object. Image distance, pole to the image. So please keep that in mind, okay? And how are these guys connected? So these reciprocals, it's not F equal to V plus U, reciprocal of focal length. So 1 by F equals 1 by V plus 1 by U, okay? Very important. And this is how you use the formula. Derivation of this formula is not required. We just need to know the formula and how to apply it. So for example, if focal length and object distance are known, we can find the image distance. So given two things, just like we solve a maths equation, you can find the third guy. If you know two things, you can solve this equation and find it. Simple. And then the next formula, so this formula is known as the mirror formula. This famous one which connects focal length, object distance and image distance, this is called our mirror formula. So let's write this down. This is the mirror formula. When you guys do the lenses chapter, it will be called lens formula, and you guys know what it will look very similar, but there's one important difference. This will become 1 by V minus 1 by U. So please be very careful of the sign. Mirror formula is 1 by F equal to 1 by V plus 1 by U. Lens formula is 1 by F equal to 1 by V minus 1 by U. So please don't mix the two. Always check, are you doing a mirror question or a lens question? It's a very common mistake. Next formula is called, do you guys know what does this M stand for? What is M? M stands for magnification here. And H dash and H, so basically what is this formula saying? M is the magnification, so magnification is the ratio of the image height to the object height, okay? So it is image height divided by object height. So that sort of makes sense, right? If the image is 2 times the object, it will be 2 by 1, 2, right? Magnification will become 2. So always image height divided by object height, this is the ratio. And let's say if image is measured in, the heights are measured in centimeter, obviously you can see the unit will cancel. So this is the magnification formula, H dash by H. Now one very interesting thing, magnification is connected to the image and object distance. How? Magnification, image height by object height. So this is our M. Image height is labeled as H dash. In some of the books it might be written as HI for image and HO for object height, or H dash and H. So whichever convention you are using, and that is equal to image distance by object distance but with a negative sign. So again, please don't forget this sign, otherwise your answer will be wrong. Okay, so this is the other important formula, and that's why it is called as magnification formula, because it is connecting the magnification. The image height by object height, this is the basic formula, but it's also connecting it to image distance by object distance. So this is our magnification formula. Very important. Please write and learn these formulas. The best way to learn the formulas, write it down and keep using it in the questions. And whenever you're doing the sums, please write down the formula, then substitute. Don't directly substitute. Okay. HT stands for height, image height by object height. Now, one very important thing, when we are using these formulas, we have to follow a sign convention. This is super important, because if you write the wrong sign, gone. right? You did everything right, but one sign mistake, the whole answer will be wrong. So let's carefully understand what is sign convention. I've explained it in my video also in detail. Please watch that previous video. Here we'll do a quick recap. So we are using the example of concave mirror here. You can see this is the back part of the mirror, and these are these three important points. Pole is the center of the mirror. This is the center of that curved circle, which is called center of curvature, C, and then you have the focus here, which is exactly in the middle of pole and center of curvature. Okay. Now what does the sign convention say? One thing about very important is when you're measuring image and object distance, they are measured from the pole. Okay. So according to sign convention, distances that you measure to this left side, they are negative, and to the right they are positive. So how can we easily remember that? It's as if you are placing the coordinate axis at the pole. You have done coordinate geometry, you know there's the x horizontal axis and y the vertical axis. So please place those coordinate axes here where the origin is at the pole. Okay, so I want all of you to draw the coordinate axis like this. This is my y axis and this is our x axis. So this positive y-axis we label as y, negative y-axis y dash, positive x-axis x, negative x-axis x dash. This is our pole, focus and center of curvature. So can you guys see pole is like the origin where the x and y axis meet? So what does sign convention say? Any distances you are measuring to the right, that means along the positive x-axis, these distances are considered positive. Anything measured here is negative. And remember, all measurements are taken from the pole. So you measure just like this, just like coordinate geometry, you measure from the origin, same way over here. Okay. And when you're measuring heights, so object height, image height, then you will be measuring along the y-axis. That makes sense. So anything measured upwards. So if the object is upright, usually the object will be upright. So all these heights will be positive. But anything which is inverted, like we can get an inverted image, they will be negative. So once again, they are measured again from the principal axis you are measuring. Anything above positive, anything below negative. This sign convention is super important. So the easiest way I remember sign convention is I draw this rough diagram, concave mirror, convex mirror, whatever sum you're doing, make sure you draw those coordinate axes, because when you draw the coordinate axis, automatically your coordinate geometry brain starts working, you start thinking positive, negative. Okay, otherwise the whole thing will go wrong. So be very careful of that. Yes, and this is looking like the Cartesian plane with the 4 quadrants. Very good, Shiva. Very good, Jitesh. Exactly. The same sign convention works for convex mirrors also. So here once again, you will draw your coordinate axis at the pole. So remember, again we have pole, focus and center of curvature. And remember I told you guys that this PFC is, there's a mistake in that previous video. We will have it corrected, okay, hopefully by next week. That editing needs to be fixed, but make sure these are behind the mirror in convex mirror, right? So important difference here, you can see in a concave mirror, the PFC are in front of the mirror. Why? Because this is the center of the circle. Obviously it should be here. So PFC should be in front of the mirror. Here this circle completes like this. So this will be the center of the circle. So PFC will be behind the mirror. So this is very important for you guys to remember. Now please draw the coordinate axis. So coordinate axis will be like this. This is my x axis. So x and x dash. Y and y dash. So remember, the pole is the origin. Your focus is exactly halfway between pole and center of curvature. So once again, if we measure distances this way,
from the pole this way, will they be positive or negative? According to sign convention, this is called sign convention. So as you can see, these distances are measured along the positive x-axis. So definitely they will be positive. Now if you are measuring some distances this way, this is along the negative x-axis, negative for sure. If you are measuring heights above the principal axis, definitely positive, because positive y-axis. If you are measuring below the principal axis, right, you're going down here, definitely they'll be negative. So this is important. Always draw this axis. You'll never forget the sign convention. So for example, if an object is kept here at, let's say, a distance of 5 centimeters, what will be the measurement? Will we write +5 or -5 if an object is kept over here? Very good, -5, because you can see it's on the negative x-axis, right? If an image is formed here, let's say an image is formed somewhere here. Let's say it's at 4 centimeter, so +4, because it's along the positive x-axis. Clear? So we have to follow the sign convention, the distance, right? Similarly, if it's an upright object, positive height. If the image is upright, positive. If it forms an inverted image, negative height. So let's practice this sign convention and the mirror formulas using sums, because in today's class we are going to focus on sums, and I'm going to show you some very easy important tricks. If you use that, you'll get it right. Okay, so please try to follow these tricks and I'm sure you'll not make a mistake. So let's start with the first question. An object of height 5 centimeters forms a real image of height 2 centimeters in a spherical mirror. Find the magnification. So can you guys do this for me? An object of height 5 centimeter forms a real image of height 2 centimeter in a spherical mirror. Find the magnification. So always whenever you're doing sums, first thing is read the sum carefully, note down all the data and use the kind of symbols, the standard symbols that you know, like U, V, F or H, H dash, right? Because that will relate you to the formulas. That way you can easily remember the formulas if you write it in terms of standard symbols. So let's read here. Object of height 5 centimeter. So that means object height is given. So object height we denote usually with H. Forms a real image of height 2 centimeter. So you can see it's forming a real image of height 2 centimeter. That means H dash is image height is 2 centimeter. In a spherical mirror, so they haven't told us whether it's a concave or a convex mirror. So it could be either. But which one do you think it will be? Real image who gives? Concave or convex mirror? Can you guys tell me? Who gives a real image? A concave or a convex mirror? Very good. Correct answer is only concave mirror can give real image. Convex mirror only gives virtual image, which means only the image can form behind the mirror for convex. Concave mirror can give real image. Very good. So that's another thing that you guys know. And now the question is find the magnification. So we need to find what is the magnification here. So if you guys remember what is the formula for magnification? See, we are going to use that simple magnification formula. M is H dash by H. So that's it. We'll just go ahead and use it. So let's go ahead and substitute the values here. Magnification is H dash by H, 2 centimeter by 5 centimeter. So 2 by 5, which is magnification is 0.4. So is this the correct answer? Many of you are thinking no. So this is what I told you. Sign convention is very important. Do not just write down the data. You need to write the data with the correct sign. So what is the mistake we have done here? So let's read it carefully. Object of height 5 centimeter. Now they haven't told us whether the object is upright or inverted. But usually object is upright. Otherwise they would have said inverted object, right?
So if an object is upright, that means it's along the positive y-axis. So this sign is correct, positive. In fact, to remember it, you can even write +5. So that means you have thought of the sign. So you can write H is +5. Why? Because it is upright. You don't have to write the reason. This I'm just telling you to explain you. What about the image? Image, you can see it clearly says it forms a real image. Now real images, are they upright or are they inverted? This is very important rule. Real images are always inverted. Real images are always upside down, inverted. Virtual images are always erect or upright. Okay, so that means real image means it must be inverted. So if the image is inverted, it's along the negative y-axis. Yes, so it has to be, you have to write it with the correct sign. So all this data has to be with the right sign. It should be -2 centimeters because it is a real and inverted image. They won't tell you in the question, please write -2. You have to work out the correct sign. It's like, somebody made a loss of ₹100. So you write profit is -100 if you are writing profit. Same thing over here. So now when you find the magnification, everything was correct here except this sign, right? So this is this is -2 centimeters. So see, this will be negative here. Minus, and so magnification will turn out to be negative. Very, very important. So your final sign is very important. -0.4 is the correct answer. Usually we write it as decimal in physics rather than fraction. So what is the meaning of this negative magnification? Always whenever you're looking at the magnification number, consider the sign separately and then the number. The negative tells you that it is an inverted image. So this minus part tells you, because there is a minus means image is inverted. And since the number is 0.4, lesser than 1, that means what type of image it is? Because magnification is image height by object height. Now since the number is less than 1, this means it is a diminished image. Size of the image is smaller than the object. That's why the ratio is 2/5, not 5/2. Clear? So that's how you understand. That's the meaning of that final number. -0.5. Minus means inverted image. 0.4 means diminished image. Next question. The magnification produced by a mirror is -1.5. What does it signify about the image formed? Which type of mirror can produce this image? So like we were discussing, look at that magnification number, break it down and try to solve this. So what have they told us? Magnification is given as -1.5. So M is -1.5. So split it up, sign and number. Negative means what? It is an inverted image. 1.5 or 3/2. What does this tell you about the size of the image? Is it magnified, inverted, or same size? What do you guys, magnified, diminished, or same size? What do you guys think? Clearly it's bigger than 1. The ratio is bigger than 1. That means image is bigger than the object because it is a ratio, right? Image by object. So if that ratio number is bigger than 1, clearly it is magnified. So we can clearly say it's a magnified image. Because it is inverted, what type will it be? Real or virtual? Inverted means the right answer is it will be a real image. So what does it signify about the image? We can say, therefore image is real, inverted and magnified, and you have to give your reasons, right? Because the negative sign, the number is greater than 1. Which type of mirror can produce this image? So again, because we are doing spherical mirrors, sometimes they may ask plane mirror, concave mirror, convex mirror. So which type of mirror will form this magnification? So very good. Once again, we get the clue, because negative magnification means it's a real image, inverted image. Convex mirror never forms an inverted image. It never forms a real image. So definitely this has to be concave mirror, and concave mirror produces magnified image. Convex mirror, it's always diminished. So both things are telling us definitely it's a concave mirror. So answer is concave mirror. And please think carefully. Sometimes you're thinking concave but writing convex, or thinking the opposite. Clearly it will be a concave mirror here. Next question. An object 3 centimeters high is placed at a distance of 10 centimeters in front of a concave mirror of focal length 20 centimeters. Find the position, nature and size of the image formed. So now the real sums are coming, because those sums were very simple. They were just magnification based, formula based, right? Now it's really coming that, object distance, image distance, finding those kind of things. So that means we have to use maybe mirror formula or maybe magnification formula as well. So now let's see how to solve this. And what is the simple trick here? Rather than, just directly applying formula and doing something, first important trick is the DAD trick. What is DAD trick? Draw a diagram, or rather draw a rough diagram, because you have not been asked to draw a perfect ray diagram, with all the rays and all of that. That was done in a separate class. So first thing, draw a rough diagram, because that will help you visualize the problem, and that will help you check the signs. Because remember, all these numbers U, V, F, we have to write with correct signs, just like we did with magnification. One sign mistake, gone. So you don't want to do that. Okay, so first step, all of you, please promise me, let's draw a rough diagram. Don't jump into the well, don't jump into the sum. Okay, so what is the thing given here? Let's look at the data. It says, okay, there's a concave mirror, some things are given. So let's draw a rough diagram. Again, it's rough. So let's go ahead and do a rough diagram here. That we have been told there's a concave mirror, and object 3 centimeters high is placed at a distance 10 centimeters in front of a concave mirror, focal length 20 centimeters. Okay, so here we can mark the pole, focus, center of curvature. So it says the concave mirror focal length 20 centimeters. So let's mark that. Focal length means distance from pole to focus. So this is given to us 20 centimeters. Object is placed at a distance of 10 centimeters. That means between pole and focus. So somewhere here. Object height 3 centimeters. See again, rough diagram. Okay. Now one very important thing, when you draw the rough diagram, please draw that coordinate axis, that sign convention axis I told you, otherwise you'll forget to take the signs. So please do that right now. So we are going to draw our x-axis here and the y-axis. Okay, so this will remind us to take all the distances and heights with the correct sign. So has everybody done this? Please draw the rough diagram. And width. With these coordinate axis or sign convention axis. Now let's write down the data, because here we don't have to write the plus minus, this is just for a visualization. Now we can think of the plus minus based on these coordinate axis. So let's quickly write down the data here. So what is given to us? Object 3 centimeters high. So everything you're reading, you note it down in your data. So object height, that means this is object height, we'll denote it with capital H. It says 3 centimeters. Should I take it positive or negative? Based on our rough diagram, what should I take? Positive height or negative height? What do you guys think? Very good. Clearly you can see the object is along the, if we call this object AB, it is clearly along the positive y-axis. So definitely object height, and put this plus. I know it sounds silly to put plus, but it will remind you, hey, I thought of the sign. Okay, I didn't miss the sign. Plus 3 centimeters. So these are the tricks, that don't miss out on any sign. Otherwise you will miss out on the marks or your sum will go wrong. So plus 3 centimeters, object height. Next thing given, so this part is done. It is placed at a distance of 10 centimeters in front of the concave mirror. So when we look back here, 10 centimeters in front of the concave mirror, that means this is object distance. We are talking about the object. Distances are measured from the pole. So object distance means U. That is the symbol of object distance, 10 centimeters. What sign should I put here? Again, keep thinking, positive or negative, positive or negative. So according to this is clearly along the negative x-axis, simple coordinate geometry. This is your origin, the pole is like the origin. I am measuring from here. So it is along my negative x-axis, definitely minus 10. Okay, done, see? So we have done that. Next, let's look at focal length 20 centimeters. Focal length means small f, 20 centimeters. Again, positive or negative. You don't have to memorize this. If you have this drawn in front of you, you will easily get the sign. So again, the pole is like the origin. Focal length means distance from pole to focus. So is it along positive or negative axis? Because remember, you're not going from focus to pole. You're going from pole to focus. Always you're measuring from the pole. Always you're measuring from the pole. Pole to focus. Very good. Negative x-axis, minus 20 centimeters. So is everybody comfortable with this data? So we have noted what all we want, and then it says what? Find the position, nature and size of the image formed. So what do we need to find here? Position means we need to find image distance. So that is unknown. Size, which means we need to find the image height. Again, unknown. So you can put a question mark. So for the things that are unknown, do I need to worry about the sign? Do I need to write plus or minus here? No, it's just like mathematics. Unknown is x. We don't think plus x or minus x, right? We just write, okay, unknown. So here you don't have to worry the sign. But the things which you're writing, the data that is given, you have to write positive or negative. So let's go ahead and work that out. And based on, these properties, we can guess the nature of the image. Is this crystal clear to everyone? Are you guys all clear about this? So please note this down. Please draw the rough diagram. I don't want anyone being lazy or taking shortcuts. Please practice it this way in my classes, and when you're doing it, trust me, you guys will get your questions correct. Everybody, don't be lazy. Please pick up your pen and paper. Now you have got this. Now you know that, okay. So everybody, please write down the data like this. You'll get the sums right. Trust me on this. Now let's go ahead and write down the mirror formula or whatever magnification formula. So most probably we need mirror formula here. Why? F and U are known, V is unknown. Okay. So let's write down our mirror formula, plug in these numbers and solve the question. So there you can see we are going to write the mirror formula for this guy. So we have already drawn the rough diagram here. The rough diagram is already done for us. So mirror formula is 1 by F equals 1 by V plus 1 by U. Okay. And so focal length we saw was on the negative x-axis. So focal length was minus 20. The image distance we need to find. So that's our unknown. And object distance, remember, we took it as minus 10. So that's it. You just have to solve this equation, which means you have to solve for V. So please go ahead and do that. So we can bring the 10 over here. So 1 by 10 minus 1 by 20 is 1 by V. So please take the LCM over here. 20 is the LCM. 2 tens are 20, 2 minus 1. So this is 1 by V. So therefore, what do we get here? 1 by 20 is 1 by V. So what is the image distance? (20 centimeters). All of you got this? 20 centimeters. Now is it positive or negative? Positive, which means image is formed. If we go by the sign convention, image is formed along the positive x-axis. And did we expect that in this concave mirror? Did you guys expect the image to be formed in the positive x-axis, which means behind the mirror? Yes or no? Tell me. Because clearly you can see, what case is this? Where the object, see, without solving, the object is between pole and focus. That means this is shaving mirror case or makeup mirror. So we will get a magnified image and which will be behind the mirror. So it looks absolutely right that because the object was placed between pole and focus, image will be formed behind the mirror. This answer at least is making sense, right? So we have found the image position. So this one is done for us. Now we need to find the size of the image. How do you find the size? Using magnification formula. Magnification is h dash by h. So magnification h dash by h is minus v by u. Remember? So let's go ahead and find the image height. So image height is unknown, h dash, object height h is 3 centimeter minus v by u. So v is 20 and u is minus 10, again with the correct sign. See, minus 10. So when you substitute that, what are you getting? The minus minus cancels. So this will cancel out here. And so we are going to get h dash is going to be 6 centimeters. Not minus 6. Minus minus will cancel because the magnification formula has a minus v by u. See, that's why each and every sign is very important. So this is our image height. Therefore, what is the conclusion about the image? So we can say image is, because it is a positive image height, means image is upright. That means it must be virtual. So image is virtual and upright, or you can write virtual and erect, right? Upright means it is straight. So image is virtual and upright. Why? Because positive height. Otherwise you would have got negative height, right? So this is clear. Then what we can say, image is formed 20 centimeters behind the mirror. That is the placement of the image. Image is formed 20 centimeters behind the mirror. And what else here? So these things we have got. And the last thing, size of the image. It is magnified and in fact double the size, right? Object was 3, image is 6. So image height is 6 centimeters, which means it is magnified. So of course you guys can write it in different way also. You can say image is virtual, erect, magnified, then give the details, whatever format you're following in school, but you must give all the details about the image that you have found or you have been asked to find. Clear? So this is how we solve these questions. Let's try another one. This time a convex mirror question. Convex mirror has focal length of 10 centimeters. Where should the object be placed to get an image that is half the size of the object? So again, what is the first step? Sketch a rough diagram like this. So always remember, what is the first step you guys promised me? You will draw a rough diagram. So first thing, draw a rough diagram with sign convention axis. This is super important, guys. If you don't do this, your question can go wrong. Very important. That's why check carefully. Are you doing concave mirror, convex mirror? because things can go haywire if you do the wrong mirror. Second thing, write the data with the correct sign and then use the formulas and solve. If you guys follow these 3 simple steps, I'm sure you can crack any of these mirror formula questions. And same things will apply when you come to lens formulas for concave and convex lenses. Same tricks. Okay. So let's go ahead and quickly do this one. So first thing is you should draw a rough diagram. So I've just sketched something here out like this. So you have your pole, focus and center of curvature. We can see that convex mirror has a focal length of 10 centimeters. So let's mark that here. Pole to focus is 10 centimeters. Where should the object be placed to get an image that is half the size of the object? So now we don't know where it should be placed. So let's randomly place it, because after all, this is a rough diagram. We can just place it anywhere. So let's say object is placed here and it says it is half the size. So that means, for example, if this is 2 centimeter object, this will be 1 centimeter. Just as an example. But nothing, no real numbers are given. That is just to understand the scenario. Okay. So this is what we have here, clear? Again, what is the important thing? When you draw this rough diagram, please make sure you guys draw the coordinate axis, that sign convention axis. So let's draw that here. This is going to be my x-axis. And they are all drawn at the pole. Okie dokie. So we have got our coordinate axis here, right? Make sure you mark that pole, which is like the origin, the focus, center of curvature. Now quickly write down your data in terms of this rough diagram. So if you guys see here, what is our focal length? 10 centimeters. Plus or minus, what sign should I put here, guys? Focal length, can you guys tell me? Positive or negative? Clearly you can see focal length is this thing from pole to focus along the positive x-axis. So plus 10 centimeters, definitely. Where should the object be placed? So as you're reading the question, see, what are they asking? Object distance. So that the image is half the size of the object. So in convex mirror, at least we know image will be inverted. If the, image will be upright as I have drawn, right? Convex mirror always gives upright image. So if image is upright, what will be the magnification sign? Positive or negative? Object is always usually upright, right? So upright, clearly magnification should be positive. Negative magnification means inverted, doesn't mean small, inverted image. So clearly magnification will be positive here. But the image is half the size of the object. So can you guys tell me what will be the magnification? If image is half of the object, what is the ratio going to be? Half, 0.5, right? So we can simply say magnification is going to be half, again with that plus sign. That means I have taken the sign. Clear? So that's all the stuff, and we have to find u. Now there's no direct formula that connects focal length, u and m. So what do we do? But we know that magnification, there is some formula, right? Magnification formula is h dash by h, which is minus v by u. Be careful, there's a negative sign is there. Mirror formula, it's all positive. Here there's negative. So if you have h dash by h is minus v by u, but we know that magnification ratio is half. So I can see that I'm making some connection between v and u. Yes? So therefore I can say that half equals minus v by u, or we can say that u is minus 2 times v. Does this make sense? U equals minus 2 times of v. Now we can use mirror formula, because maybe we can connect fu, and we have one equation here that u is minus 2 times v,
maybe we can use that. So let's go ahead and try it out. So I'm going to write the mirror formula first. 1 by f is 1 by v plus 1 by u. Focal length we saw was plus 10. So 1 by 10 is 1 by v plus 1 by u. But what is the connection here? U is minus 2 times v. So maybe we can substitute u. We can replace it with minus 2v. Or you could replace the v with, u by 2 based on that, right? So I'm just going to substitute. So we have u is minus 2v. So let's put that. So based on this you calculate v, and then you can calculate u, or you could have done directly, you could have changed the v into a u, whichever way you want to go. So here how will you guys do? Please do this carefully. This is 1 by 10 is nothing but 1 by v minus 1 by 2v. So maybe you can take the 1 by v common. So smart way of solving this is 1 by 10 is 1 by v, and this becomes a 1 minus a half. Yes. So 1 minus half is nothing but half. So 1 by 10 is nothing but 1 by v times half. So v is nothing but 5 centimeters. Clear? So I just took the 1 by v in common. I was left with 1 minus half, which is half. So v is 5 centimeters because 2v is 10. But I want my u because it's asking where should the object be placed. It's not saying where will the image be formed. But what is the connection? U and v are connected. So using 1, u equal to minus 2v. So now we can say using 1, u equal to minus 2v. There you go, minus 10 centimeters, and we are done. So what is the meaning of minus 10? How will you write the answer? You better not to just leave it like that, better to write in sentence form. Therefore, the object should be placed 10 centimeters. Why is it negative? Because it's on the negative x-axis. So object should be placed 10 centimeters in front of the mirror. That's how you write your answer. So we can write therefore object should be placed 10 centimeters in front of your mirror. That's it, done. So see, when you draw a rough diagram, you just do the steps, write down your formulas, you can easily solve these questions. I think one last question, let's try it out. A concave mirror produces a 3 times upright and enlarged image of an object placed at 10 centimeters in front of it. Calculate the radius of curvature of the mirror. So once again, draw a rough diagram, write down your data and try to solve this question. So see, rough diagram will involve a concave mirror. So we will mark the pole, focus, center of curvature of the mirror. What does it say? Concave mirror produces a 3 times upright and enlarged image of an object placed at 10 centimeters in front of it. So when does a concave mirror produce enlarged and upright? Can you guys tell me? So maybe we can use our case knowledge. Of course, you can draw a rough diagram without thinking about that, but it helps to think. So when does a concave mirror produce an enlarged image which is upright? Which means it's not inverted, it is upright. It is upright means it is virtual. So this is again that shaving mirror or makeup mirror case. So we know that definitely
object will be between pole and focus of the mirror. See, there are the clues in the question. So we know that our object will be somewhere here, because this is clearly a shaving mirror case. Right? So we are clear about that. Object 10 centimeters in front of it. So let's mark the object distance given is 10 centimeters. And it says it produces 3 times upright and enlarged image. So if you look at this, since it is 3 times, we know what will be the magnification? +3. Why did I write +3? Because 3 times, and positive because upright image. Negative means it is an inverted image. So positive magnification means image is upright. Clear? So we have written this, and now we know that object distance given to us is 10 centimeters. But again, sign convention, so please don't forget to draw this sign convention axis. We have x, x dash, y, y dash. So clearly object distance positive or negative? Object is along the negative x-axis, it's in front here, right? So along the negative x-axis, -10. Clear? And what do you need to find? Radius of curvature of the mirror. So we don't need to find, we need to find the capital R, radius of curvature. Remember, there's a formula connecting radius of curvature and what? Focal length, because we know it's twice the focal length. So basically we need to find f and double it, right? So actually we need to find focal length, and that will lead us to the radius of curvature, 2f. That's it. So how will you guys do this? Come on. So you can see some magnification is given. That means we can use magnification formula. So we know magnification m is minus v by u. 3 is, yes, minus v by u. But u is given to you, -10. So please substitute it here. The minus gets cancelled. So what is the image distance? 30 centimeter. 30 means plus, so it's along the positive x-axis. That is exactly what we expect, because in a shaving mirror case, we expect the image to be formed behind the mirror. We expect this 3 times magnified to be here. So that definitely makes sense. 30 centimeters image distance, 10 centimeters object distance. All we need to find is focal length. Let's use mirror formula for that. So using mirror formula, 1 by f is 1 by v plus 1 by u. The image distance we found was 1 by 30, and the object distance is -10, right? See, very important to use the correct sign. -10, this one is positive. So just go ahead and solve this equation. Just solve for f. So, or 1 by f is basically going to be 1 by 30. You can bring this minus up here. So minus 1 by 10. Please take the LCM. LCM is 30. So 1 minus 3. So what are we getting? Focal length we are getting -15 centimeters. Does that make sense? Because for a concave mirror, focal length should be negative. It should be along the negative x-axis. So see, you can check, is your answer making sense according to sign convention? Absolutely. So what is going to be the radius of curvature? Very simple. Therefore, we can say R is 2f, 2 times -15. So therefore, r is going to be minus 30 centimeters. Once again, you can end your answer with the radius of curvature therefore is 30, because you can give both the numerical answer with the sign and then the written answer. So therefore we can say radius of curvature of mirror is 30 centimeters. So I would say to give both the answers, the numerical answer with the sign and then the written answer as well. So that's it. The trick was draw a rough diagram, visualize the question, please draw that sign convention axis, positive, negative axis, write down the formulas clearly, write down the data with the correct sign, and then just use your formulas, and please learn these formulas, write them down, and it's super easy. After that, it's just solving it. So once again, draw a rough diagram with sign convention, write down the data with the sign convention. Keep asking yourself, positive or negative? If it's unknown, you just leave it as is. You don't need to think about the sign. And then you saw that we were doing some common sense there. We were checking, okay, does this, should the focal length turn out to be positive, or should the, image distance be positive or negative? You should definitely check that while solving. So even without, checking the numerical, just the sign. So sign convention is super important, and all these formulas have to be used with sign convention. So hope you guys enjoyed this class, and if you follow this technique, I'm sure you'll get all these sums right. So please practice and use this technique, okay? Do not do shortcuts.